Picture a world so vast it could swallow our own planet more than 700 times over. A world adorned with a breathtaking halo of ice and rock that has captivated humanity for centuries. Gaze into the night sky on a clear evening, and you might catch a glimpse of that distant, pale jewel Saturn, the crown jewel of our solar system. But what secrets lie hidden within its majestic rings and swirling storms? We are about to embark on a journey to the very edge of human understanding, to a gas giant that defies simple explanation and holds mysteries that challenge everything we think we know about the cosmos. This isn't just a story about a planet. It's an exploration of the profound and sometimes unsettling unknowns that linger in the dark, waiting for a curious mind to uncover them. From the moment Galileo first trained his primitive telescope on this celestial wonder, mistaking its rings for strange handles, Saturn has been a source of awe and bewilderment. It's a world of unimaginable extremes where hurricanes larger than our entire planet rage for decades, and where the very rings that make it so iconic are whispering clues to a violent, chaotic past. Each new mission, each photograph beamed back from the cold depths of space, seems to answer one question only to present us with 10 more. The feeling is one of both incredible discovery and humbling insignificance, as we realize that for all our technology and knowledge, we have only just begun to scratch the surface of what this giant holds. In this video, we will venture together through 25 of Saturn's most baffling and compelling mysteries. We will unravel the strange hexagon spinning at its north pole, a geometric storm so precise it seems almost artificial. We will dive into the theories surrounding its enigmatic moons, worlds that may hide oceans of liquid water and just maybe the conditions for life. We will confront phenomena that have no clear explanation, puzzles that have stumped the brightest minds for generations. This is a journey of scientific discovery and pure cosmic wonder, a testament to the enduring human spirit that looks up at the stars and dares to ask, what if? So settle in and open your mind, because the secrets of Saturn are stranger and more wonderful than you could possibly imagine. Our journey begins with a feature so geometrically perfect and so utterly alien that when scientists first saw it, they could hardly believe their eyes. Imagine a hurricane, but one so vast it could swallow our entire planet 4 times over. Now reshape that swirling vortex into a near-perfect hexagon, a 6-sided figure with sides each longer than the diameter of Earth, rotating majestically around Saturn's north pole. This is not a computer simulation or an artist's rendering. This is the stark reality of a phenomenon that has defied simple explanation for over 4 decades. The story of Saturn's north polar hexagon is a tale of 2 robotic explorers, one that gave us a fleeting, blurry glimpse and another that revealed its full, staggering glory. The first hint came in the early 1980s when the Voyager spacecraft flew past the ringed giant. The images it sent back were grainy and low resolution, but they contained something peculiar, an odd hexagonal pattern in the high-altitude clouds. At the time, the data was so uncertain that many dismissed it as a processing artifact or a temporary trick of the light. It wasn't until the Cassini mission arrived at Saturn in the 2000s, armed with far more sophisticated cameras and sensors, that the truth was confirmed. There it was, not just a fleeting illusion, but a permanent, towering structure in the atmosphere. Cassini revealed the hexagon to be a jet stream, a river of air racing at over 300 miles per hour, with its 6 distinct sides acting as walls that contain the violent weather within. Perhaps the most mind-bending aspect is its longevity. This colossal geometric storm has been churning, stable and unchanged for at least 40 years and possibly much longer. What natural process could possibly create and maintain such a precise shape on such an unimaginable scale for such an immense period of time? Scientists have proposed several theories, with the most prominent suggesting it's a type of standing wave pattern. Think of it like the stationary wave that forms when you stir a cup of coffee, where the fluid motion creates a specific, stable pattern. In Saturn's case, the deep, churning atmosphere might act as a fluid, and the planet's rapid rotation, a day on Saturn is only about 10.5 hours long, could generate this six-sided waveform. The mathematics behind this is incredibly complex, involving the different rotation speeds of atmospheric layers and how they interact to create a stable polygonal shape. Yet, while this theory can produce hexagons in laboratory simulations, replicating the sheer scale, stability, and perfect geometry of Saturn's version remains a monumental challenge. It raises a deeper, more profound question: why a hexagon? Why not a pentagon, an octagon, or just a typical circular storm? The specificity is what continues to baffle researchers. This isn't just a cloud formation, it is a monumental atmospheric puzzle, a natural structure of such perfection that it almost feels designed. Its existence forces us to reconsider the fundamental forces at work within gas giants, reminding us that the laws of physics can manifest in ways far stranger and more beautiful than we typically experience here on Earth. The hexagon stands as a silent, spinning sentinel at Saturn's pole, a testament to the planet's dynamic and utterly mysterious nature. Moving from the geometric perfection of the hexagon, we encounter a mystery that isn't about a visible shape but an invisible force, a pervasive and unexpected heat that envelops the entire planet. If you were to journey high into Saturn's upper atmosphere, you'd expect it to be bitterly cold. After all, Saturn orbits nearly 10 times farther from the Sun than Earth does, receiving only a tiny fraction of the sunlight that warms our world. Based on solar heating alone, scientists calculated that the upper layers of its atmosphere should be a frigid -280 degrees Fahrenheit. But when the Cassini spacecraft took direct measurements, it revealed a shocking reality. The temperature was a scorching 800 degrees, hundreds of degrees hotter than any model had predicted. It's as if you walked into a walk-in freezer only to find it as hot as a pizza oven. This discovery sent Planetary scientists back to the drawing board, confronting a fundamental question: what unseen furnace is cooking Saturn's upper air? This isn't a minor discrepancy, it's a major flaw in our understanding of planetary energy budgets. For decades, the conventional wisdom was simple: a planet's upper atmosphere is heated primarily by the sun's ultraviolet light. But on Saturn, that solar input is far too weak to account for the intense heat we observe. Something else, a powerful and continuous internal heat source, must be making up the difference. This phenomenon, known as the energy crisis, isn't unique to Saturn, Jupiter, and even some distant exoplanets show similar unexpected warmth. But Saturn's case is particularly extreme, making it the perfect laboratory to solve this cosmic whodunit. The prime suspect in this investigation is Saturn's spectacular auroras. Just like Earth's northern and southern lights, these dazzling displays are created when charged particles from the solar wind are funneled by the planet's magnetic field and slam into the atmosphere near the poles. This process releases a tremendous amount of energy. The leading theory, often called the auroral heater model, suggests that this energy doesn't just create light. It also generates powerful winds and giant waves that ripple outward from the poles toward the equator, distributing heat across the entire planet like a global atmospheric conveyor belt. Cassini's data did find evidence of this, with hotspots centered on the auroral zones. However, the puzzle isn't completely solved. While the auroras are undoubtedly powerful, many researchers question whether they are powerful enough to heat the entire globe to the extreme temperatures we see. The search for other contributing factors is wide open. One compelling alternative points the finger inward toward the planet's deep, churning interior. Gas giants like Saturn are still slowly contracting under their own immense gravity, and this contraction generates heat from the inside out, a leftover from the planet's formation over 4 billion years ago. Theoretically, this internal heat could rise upward and somehow be deposited in the upper atmosphere, though the exact mechanism for how this works remains unclear. Another fascinating idea involves currents within Saturn's own magnetic field, suggesting that energy is being dissipated directly into the atmosphere through a process called Joule heating, similar to how an electric stove coil glows hot. What makes this so complex is that these processes aren't mutually exclusive. It's likely a combination of auroral energy, internal heat, and magnetic friction all working in concert, a symphony of heating that we are only just beginning to decipher. Cracking this case is about more than just solving a puzzle for one planet. Understanding where Saturn's excess heat comes from is crucial for building accurate models of how all gas giants, including the hundreds we've discovered orbiting other stars, form and evolve over billions of years. The heat a planet retains tells a story about its birth, its composition, and its internal dynamics. If our models are wrong about something as fundamental as an energy budget, then our entire understanding of these majestic worlds could be built on a flawed foundation. This invisible thermal anomaly is a stark reminder that even the most basic assumptions about how planets work can be upended by a single, precise measurement from a robot explorer millions of miles away. From one invisible process to another, we now turn to a discovery that reframes our entire understanding of Saturn's most iconic feature. We often picture the rings as a permanent, eternal crown, a timeless part of the planet's identity. But groundbreaking research has revealed a shocking truth. Saturn's rings are dying. They are not a permanent fixture. They are a transient, dazzling spectacle in the grand timeline of our solar system, and we are witnessing them in their glorious but fleeting prime. The most stunning part of this revelation is not just that the rings will disappear, but that they are actively draining away onto the planet right now in a process as beautiful as it is destructive. This phenomenon is known as ring rain. Picture the countless trillions of ice and dust particles that make up the rings. They are not simply orbiting in serene, stable paths. Instead, they are under constant assault from the sun's ultraviolet radiation and from tiny meteoroid impacts. This bombardment electrically charges these tiny particles. Once charged, they become susceptible to the invisible lines of force of Saturn's powerful magnetic field. Think of it like a cosmic conveyor belt. The magnetic field acts as a guide, pulling these charged ice grains out of their stable orbits and funneling them down into the planet's upper atmosphere. When these icy particles fall, they don't just vanish silently. As they plunge into the dense atmospheric gases at tremendous speeds, they vaporize, creating a steady, invisible drizzle of water and other compounds that is literally washing Saturn's rings away. The rate of this loss is staggering. Data from the Cassini spacecraft, especially during its final, daring grand finale orbits that took it between the rings and the planet itself, allowed scientists to measure this flow directly. The estimates are astonishing. Every half hour, enough ring material falls into Saturn to fill an Olympic-sized swimming pool. At this relentless pace, the entire ring system could be completely drained away in as little as 100 million years. Now, that might sound like an unimaginably long time to us, but on the cosmic clock, it's a mere blink. To put it in perspective, if the entire history of Saturn were condensed into a single calendar year, the rings would appear and vanish all within the span of a single day. This forces a dramatic reevaluation of their history. If they are disappearing so quickly, they cannot be 4.5 billion years old, dating back to the formation of the solar system. Instead, they must be a relatively recent addition, perhaps forming only a couple of 100 million years ago, a time when dinosaurs already roamed the Earth. The origin story for these young rings is one of cosmic violence. The leading theory suggests they are the shattered remains of a former moon, an icy body that wandered too close to Saturn. The planet's immense gravitational tides would have stretched and torn this moon apart, grinding it into the countless fragments we see today. This new timeline, where the rings are both young and ephemeral, completely changes our perspective. We are not looking at an ancient, static monument. We are witnessing a vibrant, dynamic, and highly active system in the middle of its life cycle. It is a celestial waterfall on the grandest possible scale, a cascade of ice from orbit onto the cloud tops of a giant. This realization carries a profound sense of cosmic privilege. We exist in a brief window of time, a mere sliver of cosmic history, where a planet in our own solar system wears a glorious, temporary crown. And just as we're grappling with the fleeting nature of Saturn's rings, we encounter a mystery that strikes at the very heart of the planet's identity. How long is a day on Saturn? For a world so immense, you might think this would be one of the most basic facts to know, a simple measurement. Yet, this question plunged planetary scientists into a decades-long detective story filled with false leads and contradictory clues. The challenge wasn't just technical, it was fundamental. Saturn, as a gas giant, has no solid surface. There are no mountains or craters to track as they rotate in and out of view. So, how do you clock the spin of a planet made almost entirely of clouds and gas? The traditional method for gas giants involves monitoring regular, repeating radio signals generated by the planet's magnetic field. As the planet's deep interior rotates, it drags the magnetic field along with it, creating a periodic pulse that can be measured from Earth, much like following the sweep of a lighthouse beam. This technique worked beautifully for Jupiter, giving us a precise rotation period. But when scientists turned their instruments toward Saturn, the results were baffling. The signal wasn't clean. Data from the Voyager missions in the early 80s suggested a rotation period of about 10 hours and 39 minutes, but when the Ulysses spacecraft took measurements years later, it found a period that was nearly 10 minutes longer. The planet's rotation rate appeared to be changing, which, for an object the size of Saturn, was physically impossible. The core of the mystery was Saturn's magnetic field itself. Unlike any other planet we've studied, Saturn's magnetic poles are almost perfectly aligned with its axis of rotation. This rare symmetry means the magnetic field doesn't wobble as the planet spins. It presents a nearly uniform face to an observer, making its rotation incredibly difficult to detect through the usual radio noise. For years, scientists were stuck. They knew the planet was spinning, but they couldn't find a reliable clock. The solution finally began to emerge from the incredibly detailed data collected by the Cassini mission, particularly during its final, courageous plunges between the rings and the planet. Instead of relying solely on the confusing magnetic field, researchers turned to a much more subtle measurement, the planet's gravity. As Saturn rotates, its equatorial region bulges outward slightly due to centrifugal force. This bulge subtly alters the gravitational field around the planet. By meticulously tracking how Cassini's trajectory was nudged by these tiny gravitational variations, scientists could essentially weigh the planet's bulge and from that back-calculate its rotation speed. This groundbreaking analysis pointed to a definitive day on Saturn, 10 hours, 33 minutes and 38 seconds. After decades of uncertainty, we finally had a number. But finding the answer only led to a new and perhaps more profound question. Why is Saturn spinning so fast? This rotation rate means the planet's equator is hurling through space at a breathtaking 22,000 miles per hour. This tremendous speed has profound effects, flattening the planet into a distinct oblate spheroid. It's visibly squashed at the poles and bulging at the equator. Yet, the mechanics that drive and sustain this incredible spin are still not fully understood. It's a relic of the planet's formation, a conserved momentum from the primordial cloud of gas and dust that collapsed to create it billions of years ago. But the precise interactions between the deep, solid core, if one even exists in a traditional sense, and the enormous envelope of liquid metallic hydrogen and helium above it remain a major area of active research. The planet's interior is a place of extreme pressure and exotic states of matter. and how these layers transfer energy and angular momentum to create the single, coherent spin we observe is a puzzle that continues to challenge our models of planetary physics. Solving the riddle of the day length didn't end the mystery. It simply opened a new door into the hidden, churning heart of the giant. From the fleeting nature of the rings, we are drawn irresistibly to the greatest mystery of all, their very origin. If they are indeed a temporary feature, as the evidence of ring rain suggests, then we are forced to ask a profound and dramatic question. What cosmic event occurring in the relatively recent past could have woven this spectacular, icy necklace around the sixth planet? The leading theories are tales of celestial destruction and failed creation, each with compelling evidence but no final, definitive proof. The most widely accepted and vivid theory is one of catastrophic violence, the gravitational shredding of a former moon. Imagine an ancient, icy moon, perhaps as large as Mimas or even Titan, orbiting peacefully for billions of years. Then, through some gravitational nudge, its path slowly decays, drawing it ever closer to the immense gravitational pull of Saturn. As it crosses a critical boundary known as the Roche limit, the planet's tidal forces become stronger than the moon's own gravity. The moon is no longer a single, cohesive body. It is pulled apart. Saturn's gravity would have stretched it like taffy, shattering it into countless fragments. These pieces, ranging in size from fine dust to mountain-sized boulders, would then be shepherded by Saturn's gravity into the flat, disc-like structure we see today. This theory elegantly explains the ring's predominantly icy composition, as many of Saturn's moons are largely water ice. It's a story of a world unmade, a permanent scar from a moment of incredible chaos. But there is a compelling alternative, a narrative not of destruction but of a birth that never was. This theory posits that the rings are primordial, but not in the way we once thought. They could be the leftover rubble from the original cloud of gas and dust that formed Saturn itself, material that simply never managed to coalesce into a moon. In this scenario, the proto-lunar material was scattered and torn apart by gravitational interactions within the crowded early solar system, or it was prevented from clumping together because it formed within the Roche limit, where tidal forces are too strong for a moon to hold itself together. This would make the rings as old as the planet itself. However, this ancient origin story is now in direct conflict with the new evidence of the rings' rapid decay and youthful age. If the rings were truly primordial, they would have been drained away eons ago, long before humans ever looked skyward. Their current brilliance argues powerfully for a recent dramatic genesis. The Cassini mission provided crucial data to weigh these competing ideas, focusing intently on the ring's mass and composition. By studying how the spacecraft's trajectory was minutely altered by the ring's gravity during its close passes, scientists could calculate their total weight with unprecedented precision. The result was startlingly low. The entire vast ring system, spanning over 270,000 kilometers from end to end, has a mass of only about 1/2 the mass of Mimas, one of Saturn's small, icy moons. This lightweight nature strongly favors the moon-shattering hypothesis. It would not take a colossal, Titan-sized moon to create the rings, but a relatively modest one. Furthermore, Cassini's instruments confirmed the rings are almost 99% pure water ice, with only a tiny sprinkling of rocky dust. This incredible purity is another clue pointing to a cataclysmic origin, as a differentiated icy moon would have a mostly icy mantle that would be scattered in such an event, while a more mixed primordial cloud would likely have contained a much higher fraction of rock. Yet for all this evidence, a definitive answer continues to elude us. The moon-shattering theory, while elegant, has its own gaps. What was the exact nature of this ill-fated moon, and what was the precise trigger for its demise? Was it a slow, inward spiral, or was it a single, shattering collision with a passing comet that first broke it apart? The young age of the rings suggests this event happened in what amounts to a cosmic eye blink ago, yet we see no other recent, comparable cataclysms in the solar system to confirm such events are common. The origin of Saturn's rings remains one of the most captivating open questions in planetary science, a beautiful puzzle where the clues point toward a recent, violent birth, but the final chapter of that story has yet to be written. We are left with the image of a glorious monument built from the ruins of a lost world, a permanent reminder of the dynamic and often destructive forces that shape our cosmic neighborhood. As we turn our gaze from the planet itself to its family of moons, we encounter a world so bizarre it seems to defy the very laws of celestial aesthetics. Imagine a moon that is literally two-faced, one half gleaming like freshly fallen snow and the other as dark as charcoal, creating a stark yin-yang appearance against the black velvet of space. This is Iapetus, one of Saturn's most distant major moons, and its dramatic dichotomy has been a source of intense speculation ever since its discovery over 3 centuries ago. The story of Iapetus is a cosmic detective story involving an outward-facing dark side that absorbs heat and a bright side that reflects it, a suspected thief stealing material from another moon, and a ridge along its equator so precise it looks almost stitched on. The mystery began with its discovery. Giovanni Cassini first spotted Iapetus in 1671, but he immediately noticed something peculiar. He could only see the moon when it was on the western side of Saturn. When its orbit took it to the eastern side, it simply vanished from view. Cassini correctly deduced that Iapetus must be tidally locked, meaning the same hemisphere always faces forward in its orbit, and that this leading hemisphere was somehow profoundly darker than the trailing one. For centuries, that was all we knew. It wasn't until the Voyager and later Cassini spacecraft gave us our first close-up views that the true, stunning strangeness of this world was revealed. The leading hemisphere, named Cassini Reggio in honor of its discoverer, is coated in a material as dark as asphalt, reflecting only about 5% of the light that hits it. The trailing hemisphere and the poles, by contrast, are blindingly bright, composed of almost pure water ice with a reflectivity comparable to fresh snow. The transition between these two realms isn't a gradual blending. In many places, it is an astonishingly sharp line, as if a giant cosmic paintbrush meticulously separated light from dark. So, what creates this incredible contrast? The leading theory is a brilliant piece of planetary sleuthing that involves 2 key processes: an external contaminant and an internal feedback loop that amplified the effect over millions of years. The suspect for the external contaminant is Phoebe, a dark, distant, and irregularly shaped moon orbiting far beyond Iapetus. Phoebe is constantly bombarded by micrometeoroids which kick up a fine, dark dust from its surface. This dust, spiraling slowly inward under the influence of solar radiation, creates a vast, tenuous ring that scientists call the Phoebe ring. As Iapetus plows through this ethereal cloud of dark material on its journey around Saturn, the dust preferentially coats its leading face like bugs splattering on the windshield of a speeding car. This initial coating is the trigger for the entire phenomenon, but a simple dusting doesn't fully explain the extreme difference we see. This is where the second part of the theory, called thermal segregation, comes into play. The initial dark coating on the leading hemisphere made it slightly better at absorbing sunlight. As it absorbed more energy, it grew warmer. This is the crucial step. On the bright, icy parts of the moon, any exposed water ice is stable and remains frozen. But on the now warming dark areas, the heat became sufficient to cause sublimation, the process where ice turns directly into water vapor without ever becoming a liquid. Over immense timescales, this water vapor migrated across the moon's surface, eventually reaching the colder, brighter regions, especially the poles and the trailing hemisphere. There it refroze, adding a fresh, brilliant layer of white frost. This process created a powerful, self-reinforcing feedback loop. As the dark areas lost their ice, they became even darker and absorbed even more heat, which in turn sublimated even more ice. Meanwhile, the bright areas gained more ice, making them even brighter and colder, further locking in the frost. The two faces of Iapetus effectively engineered their own extreme personalities, one sinking into a deep, dark warmth and the other ascending to a brilliant, frozen chill. While this theory is elegant and widely accepted, Iapetus is not done challenging us. Several perplexing questions remain that keep this mystery alive. The most striking is the incredible sharpness of the boundary between the light and dark regions. In many places, the transition occurs over just a few dozen kilometers, a remarkably small distance on a moon over 1,400 kilometers wide. The thermal segregation process alone would likely produce a more gradual, blended boundary, suggesting there may be other, more complex geological or chemical processes at work that we don't yet fully understand. Furthermore, the global scale, precisely aligned nature of the dichotomy is a marvel of its own. The dark Cassini Regio isn't a simple splotch. It aligns almost perfectly with the orbital leading hemisphere, a coordination that speaks to the powerful and consistent nature of the forces that shaped it. Iapetus stands as a stunning natural experiment, a testament to how a small initial change, a sprinkling of foreign dust can, through the relentless and predictable workings of physics, transform an entire world into a celestial work of art, a perfect balance of light and shadow forever circling the ringed planet. Just when we think we've seen the limits of strangeness in the Saturnian system, we encounter a small, unassuming moon that completely rewrites the rules of where life might exist. Far from the dark duality of Iapetus, there orbits a brilliant white world, gleaming like a freshly polished marble against the void. This is Enceladus, an icy satellite only 300 miles across, so small it could easily fit within the borders of Arizona. For centuries, it was just another faint point of light, a mere speck in the telescope. But then, the Cassini spacecraft revealed its secret, uncovering a mystery so profound it shifted our entire perspective on the search for life beyond Earth. Hidden beneath its frozen, cratered shell, Enceladus was screaming to be heard, speaking in plumes of water vapor and ice that erupted from its south pole in a spectacular display of cosmic defiance. The first hints were subtle. Early images from Cassini showed a world with an unusually smooth and youthful surface, glistening with a reflectivity that rivals freshly fallen snow. This was a clear sign of recent geological activity. On an ancient, dead world, the relentless rain of micrometeoroids would have darkened the ice over billions of years, pockmarking it with craters. Enceladus was different. It looked fresh, as if it had been resurfaced only moments ago, geologically speaking. But the true stunner came when Cassini's instruments looked not at the surface but just beyond it. There, against the blackness of space, the spacecraft saw towering jets of fine ice particles and water vapor erupting from a series of warm, massive fractures near the South Pole, affectionately nicknamed tiger stripes. These weren't gentle puffs of vapor, they were continuous, powerful geysers shooting hundreds of miles into space, feeding a vast torus of material that spreads out to form one of Saturn's outer rings. It was a monumental discovery. This tiny moon, with barely enough gravity to hold itself together, was an active cryovolcanic world. The implications were so staggering that the Cassini mission planners took an audacious risk. They commanded the robotic explorer to alter its course and fly directly through these erupting plumes, skimming a mere 30 miles above the moon's icy crust. It was a maneuver of breathtaking precision and scientific daring. As Cassini plunged through the shimmering curtain of ice, its mass spectrometer tasted the composition of the grains, and the data that streamed back to Earth sent shockwaves through the scientific community. The plumes were not just water vapor, they were a rich, salty broth containing sodium chloride, common table salt, as well as carbonates and, most excitingly, a suite of complex organic molecules. These included methane, propane, acetylene, and formaldehyde, the kind of carbon-based building blocks that are essential for life as we know it. It was as if Cassini had flown through the steam of a distant alien ocean and found it to be a primordial soup. This incredible finding pointed to one inescapable conclusion. Enceladus harbors a global subsurface ocean of liquid water, sealed between its rocky core and its outer icy shell. The geysers themselves are essentially giant blowholes where the immense pressure from this hidden sea forces water up through the warm, open fractures in the ice. The presence of salt indicates that the water is in direct contact with a rocky seabed, a crucial detail. On that rocky floor, hydrothermal vents could very well be active, spewing mineral-rich, superheated water into the ocean above. Here on Earth, such hydrothermal vents on our own ocean floors are teeming with life, entire ecosystems that thrive in total darkness, fueled not by sunlight but by chemical energy. The recipe on Enceladus appears to be almost identical. Liquid water, a source of chemical energy from water-rock interactions, and the essential organic building blocks. It possesses all three key ingredients for habitability. This transforms Enceladus from a curious icy moon into arguably the most promising place in our entire solar system to search for extraterrestrial life. The mystery is no longer if the moon has a habitable environment, but whether life has actually taken root within its dark, deep ocean. The potential forms of life would likely be microbial, perhaps similar to the extremophiles that cluster around Earth's deep sea vents, but the mere possibility is revolutionary. The geysers offer us a free sample, a direct delivery system from the hidden ocean to space, meaning we might not need to drill through miles of ice to search for signs of biology. A future mission could simply fly through the plume again, with more sensitive instruments designed explicitly to look for the chemical signatures of living processes. The existence of Enceladus's ocean forces us to broaden our imagination, to consider that life may not need a sun-warmed planet with a gentle atmosphere, but could instead flourish in the lightless, pressurized abyss of a small moon, warmed from within by the gentle heat of tidal forces. In the silent, frozen expanse of the outer solar system, a tiny world is shouting its potential, offering us a glimpse into one of the most profound mysteries we have ever faced. And while Enceladus hides its ocean beneath a shell of ice, another of Saturn's moons brazenly displays its liquids for all to see, presenting a landscape that is at once eerily familiar and profoundly alien. Venture past the icy plumes and behold Titan, a world shrouded in a thick, hazy orange atmosphere, a place where the very rivers run with liquid methane and the shorelines are carved not by water but by hydrocarbons. This is the only other world in our solar system besides Earth that has stable bodies of liquid on its surface. It's a place where the fundamental principles of geology and hydrology we know so well are recreated with an entirely different set of ingredients, creating a mysterious environment that both mirrors our own planet and defies it at every turn. For decades, Titan remained an enigma, its surface completely hidden from our view by a dense photochemical smog. The first glimpses from the Voyager probes only revealed a featureless orange ball. The mystery began to unravel with the arrival of the Cassini-Huygens mission. The Cassini orbiter, equipped with a powerful radar that could pierce through the opaque atmosphere, started mapping the surface, and what it found was staggering. It revealed vast, dark, smooth patches concentrated around the moon's polar regions. The Huygens probe then delivered the crowning achievement, descending through the haze in 2005 to land directly on this strange surface. The images it sent back showed a scene that could have been from a dream, a landscape of rounded, icy cobbles lying in a riverbed, clear evidence of fluid flow and erosion, but in a climate nearly 300 degrees below 0 Fahrenheit. The liquid that fills Titan's lakes and seas is not water, which would be frozen solid as rock at these temperatures. Instead, it is a mix of liquid methane and ethane, simple hydrocarbons that exist as gases here on Earth but flow as liquids in Titan's deep freeze. This creates a complete and active hydrological cycle, just like Earth's water cycle but built on methane. Methane evaporates from the lakes, forms clouds in the thick nitrogen atmosphere, and falls back down as rain, carving river channels and filling vast basins to create seas larger than North America's Great Lakes. The largest of these, Kraken Mare, is a sprawling body of hydrocarbons that could be as deep as 1,000 feet in places. When Cassini's radar scanned these lakes, they appeared incredibly smooth and radar dark, acting as near-perfect mirrors for the radar signal, a characteristic that confirms they are filled with a remarkably still and pure liquid. But within this already bizarre reality, there are features that are even more perplexing. Scientists observing the same lakes over multiple Cassini flybys noticed transient bright spots that would mysteriously appear and then vanish. These were quickly dubbed magic islands. One leading theory suggests they could be bubbles, as the seasons change on Titan, and each season there lasts about 7 Earth years the lakes warm slightly. This warming could cause nitrogen gas, which is dissolved in the cold liquid methane, to fizz out of solution, much like carbon dioxide bubbling out of a soda when you open the bottle. These large fields of rising bubbles would scatter the radar signal, creating a temporary island that disappears once the bubbling stops. Another compelling idea is that these features are actually floating solids. On Titan, when the methane-rich atmosphere and liquid interact with water ice, it can form exotic, wax-like solids that float on the denser liquid methane and ethane. These could be vast, porous floating mats of hydrocarbons that appear and then eventually sink or dissolve. The deeper questions about these lakes go beyond their appearance and touch upon their very chemistry and potential for fostering life's precursors. What complex organic molecules are being brewed in these frigid, liquid methane seas? Laboratory experiments that simulate Titan's conditions show that its atmosphere is a giant chemical factory, using sunlight to break apart methane and nitrogen molecules, which then recombine into ever more complex compounds called tholins. These tholins are thought to rain down onto the surface, potentially dissolving in the lakes or settling on their floors. The chemistry within these lakes is therefore a form of organic chemistry we have almost no direct experience with, a potential pathway for prebiotic processes that does not rely on water. While Titan is far too cold for life as we know it, its environment is a fascinating natural laboratory for understanding the kinds of chemical reactions that could lead to life in vastly different environments across the cosmos. The lakes of Titan are more than just a geological curiosity. They are a window into an alternate version of planetary evolution, a place where the familiar script of erosion, rainfall, and seas is played out with a completely different cast of chemicals, raising profound questions about the diversity of worlds that can exist and the myriad ways nature finds to create complexity. Yet another of Saturn's moons presents a mystery not of hidden oceans or methane lakes, but of a structure so odd and fragile it seems like it should not exist at all. After the stark duality of Iapetus and the erupting brilliance of Enceladus, we come to Hyperion, a world that looks less like a moon and more like a cosmic piece of pumice or a gargantuan celestial sea sponge. This isn't a body with a solid, reassuring shape. It is a jumbled, porous, and deeply cratered wanderer tumbling through space in a state of absolute chaos. When the Cassini spacecraft first beamed back close-up images of Hyperion, scientists were met with a sight unlike anything they had seen before, a surface pockmarked with countless craters, but where those craters looked less like impacts and more like the cells of a massive, rotten honeycomb. The first clue to its bizarre nature is its incredibly low density. Measurements show that Hyperion has a density roughly half that of water. Think about that for a moment. This means if you could find an ocean large enough to drop it into, this 270-kilometer wide moon would float, Such a low density indicates that Hyperion is not a solid ball of rock and ice. Instead, it must be mostly empty space. The prevailing theory is that it is a rubble pile moon, a loose collection of ice and rock fragments held together by gravity, with enormous gaps, caverns, and voids making up as much as 40% of its total volume. This porous structure is the direct cause of its unique appearance. When smaller objects strike its surface, the impact doesn't create a traditional crater with ejected material splashing out in a neat rim. Instead, the force of the collision is absorbed by the spongy matrix, literally compressing the material and punching a hole into the moon's interior. The resulting craters have a sharp, deeply etched look, as if a giant cosmic claw had repeatedly gouged the surface, leaving behind a labyrinth of dark, icy pits. This fragile construction also explains one of Hyperion's most perplexing behaviors, its chaotic rotation. Unlike our own moon, which is tidally locked to Earth, showing us only one face, Hyperion tumbles through its orbit in an utterly unpredictable fashion. Its axis of rotation wobbles so dramatically that there is no way to determine which part of its surface will be facing Saturn from one moment to the next. There is no stable north or south pole. This happens because of its highly irregular shape. It's not spherical, but rather looks like a deformed potato. Combined with its porous, energy-absorbing structure, this odd shape means the gravitational tugs from Saturn and its larger moon, Titan, don't act in a consistent, stabilizing way. Instead, they send the moon into a perpetual, dizzying spin, a state of rotational anarchy that is remarkably rare for a body of its size in our solar system. How did such a strange object come to be? The leading hypothesis paints a picture of cosmic violence on a grand scale. Scientists speculate that Hyperion is a large surviving fragment of a much larger, ancient moon that was utterly shattered by a catastrophic impact billions of years ago. In this scenario, the collision was so powerful it blew the original parent body to pieces. Most of the debris likely coalesced to form other moons or was scattered, but this one chunk, Hyperion, survived without being compacted by its own gravity. It is essentially a fossil, a preserved piece of the primordial wreckage that has endured for eons. Its porous structure is a direct relic of that violent birth, a testament to the fact that it never experienced the internal heat and pressure that would have squeezed its fragments together into a denser, more conventional world. This theory of a shattered progenitor also helps explain its orbit, which is in a resonance with Titan, suggesting a shared gravitational history. Hyperion's peculiarities don't stop with its form and motion. Its surface composition adds another layer to the mystery. The floors of its deep, dark craters are coated with a layer of reddish-black material that bears a striking spectral resemblance to the dark stuff found on Iapetus and on the distant moon Phoebe. This material is likely complex organic compounds called tholins, which form when simple hydrocarbons like methane are exposed to solar radiation. But the question is, how did this dark gunk get there, and why does it accumulate so selectively at the bottom of these pits? One possibility is that as the dark dust from the Phoebe ring drifts inward, it settles on Hyperion's surface. Because the moon has no significant gravity to hold onto an atmosphere, sunlight hitting the brighter, icy areas warms them enough to cause water ice to sublimate. This escaping water vapor may then push the dark particles across the surface, herding them into the cold traps of the deep, shadowy craters where they can no longer be moved, creating a stark, dappled landscape of bright ridges and profoundly dark wells. Hyperion stands as one of the most peculiar and enigmatic objects in our entire solar system. It is a world defined not by what it is, but by what it lacks: a solid core, a stable rotation, a conventional geology. It is a celestial underdog, a fragile, tumbling relic that has survived against the odds, offering us a direct, untouched look into the chaotic processes of collision and accretion that shaped the early solar system. Its very existence challenges our assumptions about what a moon can be, proving that in the vast menagerie of Saturn's satellites, there is room for a porous, wobbling, sponge-like wanderer that defies every expectation. Nestled within the seemingly smooth and serene expanse of Saturn's ring, the brightest of its iconic bands, there exists a population of enigmatic features that act like celestial signatures, marking the presence of hidden worlds. These are the propeller moons, or more accurately, the telltale disturbances they create. Imagine a vast, flowing river of ice particles, each grain following its own silent orbit around the giant planet. Now drop a single, large boulder into that river. The water would part around the rock, creating a wake of turbulence both upstream and downstream. On a cosmic scale, this is precisely what a propeller is. It is the gravitational wake of a tiny, unseen moonlet, an object just a few hundred meters to a kilometer across that is embedded within and moving through the ring material itself. The reason these features are so fascinating is that they represent a strange middle ground in celestial mechanics. If the embedded moonlet were large enough, like the moon pan that clears the Inca Gap, its gravity would be strong enough to sweep its entire orbital path clean, creating a definitive, dark gap in the rings. But these moonlets are too small for that. Their gravitational pull is just potent enough to perturb the tiny ring particles in their immediate vicinity, creating a distinctive, double-lobed structure that looks remarkably like an airplane's propeller. A central, partial void forms around the moonlet itself, flanked by two longer, brighter regions that are the accumulated piles of ring material that the moonlet's gravity has gently tugged into slightly higher or lower orbits. The Cassini spacecraft didn't just spot a few of these, it discovered thousands, each one a tiny flag planted by a hidden builder, revealing a whole population of unseen objects. This phenomenon is far more than just a beautiful curiosity. It is a rare and precious window back in time, allowing us to witness the very processes that built our solar system over 4.5 billion years ago. Saturn's rings are often described as an analog, a working model, of the protoplanetary disk of gas and dust that once swirled around our infant sun. Within that primordial disk, dust grains began to stick together, forming pebbles, then rocks, then kilometer-sized planetesimals. The propeller moonlets caught in the act within Saturn's rings are the modern-day equivalents of those planetesimals. They are the building blocks of planets frozen in a crucial stage of their development. By studying how these moonlets interact with the disk material around them, how they gravitationally shepherd particles, how their orbits evolve, and whether they can grow larger by accreting more material, we are essentially watching the early stages of planet formation play out in real time right before our eyes. One of the most compelling mysteries surrounding these propellers is their surprising longevity. Based on our understanding of orbital dynamics, these small moonlets should be experiencing a constant drag from the ring particles, a process called dynamical friction, which should cause them to lose energy and slowly spiral inward toward Saturn over a relatively short period, perhaps just a few million years. The fact that we see so many of them suggests that either our models of this interaction are incomplete, or there is some mechanism that is continually creating new moonlets to replenish the population. This ties directly back to the mystery of the ring's youth. Perhaps the same disruptive event that created the rings, the shattering of an ancient icy moon, also produced this vast swarm of embedded building blocks, and we are seeing the lingering population from that cosmic collision. The propellers, therefore, are not just passive markers, they are active participants in the ring's ongoing evolution, their fates intertwined with the ultimate destiny of the rings themselves. By decoding the subtle motions and interactions of these ghostly moonlets, we are reading the hidden history of the rings and, in doing so, glimpsing the foundational moments of how every planet, including our own Earth, first came to be. While we've explored the active, dynamic processes shaping Saturn today, we must now turn to a fundamental feature that defines its very seasons and appearance, a feature that itself is a fossil of incredible violence from the solar system's infancy. Picture Earth's stable, gentle tilt, which gives us our predictable spring, summer, fall, and winter. Now, imagine a world whose axis is tilted so dramatically that for nearly half of its long year, one hemisphere is bathed in continuous sunlight while the other is plunged into an endless, deep freeze. This is the reality for Saturn, which leans at a pronounced angle of about 27 degrees. This isn't a slight wobble, it's a profound cant that raises a deceptively simple question. What colossal event in the past could have knocked a planet 10 times the mass of Earth so dramatically off kilter? The answer appears to lie not in a single catastrophic impact, but in a slow gravitational dance of cosmic billiards that played out over billions of years. The leading theory, which has gained substantial support through sophisticated computer simulations, points the finger at a gravitational tango between Saturn and its distant, icy cousin, Neptune. To understand this, we need to rewind the clock to the earliest days of our solar system, a time when the planets were not the stable, sedate bodies we know today. They were newborns jostling for position within a crowded disk of gas, dust, and planetesimals. During this chaotic era, the giant planets are believed to have undergone a process called planetary migration, their orbits shifting significantly as they interacted with this vast reservoir of leftover material. According to this model, known as the Nice model after the French city where it was developed, Saturn and Jupiter likely fell into a specific gravitational relationship called a mean motion resonance. This happens when the orbital periods of two planets form a simple ratio like 2:1, causing their gravitational influences to reinforce each other at the same points in their orbits over and over. This resonance acted like a powerful engine, destabilizing the entire outer solar system. As Jupiter and Saturn pushed outward, they in turn scattered Uranus and Neptune, sending them into much wider, more eccentric orbits. The key to Saturn's tilt lies in what happened next. The theory suggests that Saturn and Neptune became locked in their own resonant interaction. As Saturn migrated, the repetitive, rhythmic gravitational tugs from Neptune over millions of years acted like a steady hand on a spinning top, gradually pulling Saturn's rotation axis over until it settled into the significant tilt we observe today. It was a slow-motion tipping, a cosmic nudge sustained across eons. This elegant theory, however, is not without its complications and open questions, making it an area of intense ongoing research. The most significant challenge is matching the precise conditions of the early solar system in computer simulations. Researchers have found that to produce Saturn's exact 27-degree tilt, the initial conditions had to be just right. The planet's own internal structure plays a crucial role. The distribution of mass within Saturn, its rocky core, its deep layers of liquid metallic hydrogen, and its extensive gaseous envelope affects how it responds to these external gravitational torques. Some simulations produce the correct tilt, while others result in too much or too little. This tells us that the story is more nuanced than a simple push from Neptune. Other factors, such as the gravitational influence of Saturn's own large moons, particularly Titan, may have also played a minor role in stabilizing or fine-tuning the final orientation of the planet's spin. The implications of solving this mystery stretch far beyond Saturn itself. If the resonance theory is correct, it provides stunningly powerful evidence for the grand narrative of planetary migration, painting a picture of a young solar system that was far more dynamic and chaotic than its current orderly state suggests. It means the planets we see today are not in their original birth positions. They are survivors of a gravitational rearrangement that saw worlds flung across space. This understanding fundamentally shapes how we interpret other planetary systems. When we look through our telescopes and see distant gas giants with strange tilts or eccentric orbits, we may be witnessing the aftermath of similar gravitational dances. Saturn's axial tilt is more than just an astronomical fact. It is a silent witness to the violent orbital history that shaped our entire cosmic neighborhood, a permanent monument to a time of planetary restlessness that ultimately created the stable system we call home today. Just as we begin to feel we understand the slow, majestic rhythms of Saturn, the planet unleashes a tantrum of such colossal proportions it can be seen from Earth with a simple backyard telescope. Imagine a storm so vast it wraps a belt of churning white clouds entirely around the planet's middle. A storm so powerful it generates lightning strikes 10,000 times stronger than anything ever recorded on our world. This isn't a fleeting squall, it is a planetary-scale upheaval known as a Great White Spot, a phenomenon that erupts with a startling regularity roughly every 20 to 30 Earth years, like a celestial alarm clock reminding us of the turbulent forces simmering beneath Saturn's seemingly serene cloud tops. The history of these colossal outbreaks reads like a chronicle of cosmic events. The first one was officially documented by an astronomer named Asaph Hall in 1876, a brilliant white feature that dramatically brightened the planet's appearance. Since then, we've witnessed these great storms erupt in 1903, 1933, 1960, 1990, and the most recent one in 2010. This pattern suggests a cycle, an internal timer that builds up energy until it must explosively release it. The 2010 storm, observed in breathtaking detail by the Cassini spacecraft, was a true monster. It began as a tiny, bright plume in the northern hemisphere, so small it was barely noticeable. But within just a few weeks, it grew at an astonishing rate, stretching until its head and tail met, completely encircling the globe with a furious band of convection that stretched over 10,000 miles wide. It was as if a seam had ripped open across the entire planet, allowing the pent-up energy from deep within to violently burst forth into the upper atmosphere. The sheer energy involved is almost beyond comprehension. These are not simple thunderstorms, they are planet-wide convective engines. The updrafts within a great white spot are so powerful they carry vast quantities of ammonia-rich water vapor from the warm, deep layers of the atmosphere up into the frigid upper cloud decks. There, the water vapor freezes, creating the brilliant white ammonia ice crystals that give the storm its name and its dazzling visibility. Accompanying this ferocious uplift is lightning of an unimaginable scale. Cassini's radio and plasma wave instrument detected the crackle of these megabolts, which radio astronomers playfully nicknamed Saturn electrostatic discharges. The energy released in a single flash is estimated to be comparable to the total energy consumption of the entire human civilization for an entire year. This is weather on a scale that dwarfs our entire world, a tempest that could swallow Earth whole with room to spare. So, what causes this planetary alarm clock to tick with such metronomic regularity? The leading theory focuses on the delicate balance of energy within Saturn's atmosphere. Picture the atmosphere as a layered cake. The upper layers, warmed only weakly by the distant sun, are generally stable and stratified. But deeper down, closer to the planet's internal heat source, things are much warmer and more turbulent. Over time, the upper atmosphere acts like a heavy lid, trapping the warmth and moisture rising from below. This creates a situation where the upper atmosphere becomes significantly denser than the layers beneath it, roughly once per Saturnian year, which is about 29.5 Earth years. This density difference becomes too extreme. The heavy lid becomes unstable, and like a pot of water boiling over, the warm, moist air from the depths punches through in a catastrophic, planet-encircling convective eruption. It's the planet's way of venting its built-up thermal energy, a necessary atmospheric reboot that restores equilibrium for another 3 decades. Yet the timing isn't perfectly precise, and this is where the mystery deepens. Why is the cycle approximately 30 years and not 20 or 40? Why do some storms start in the northern hemisphere and others in the south? The answers likely lie in the complex interplay between Saturn's seasonal cycle and its internal heat flow. As Saturn slowly orbits the Sun, each hemisphere experiences decades-long seasons of summer and winter. The changing angle of sunlight may subtly influence the stability of that atmospheric lid, perhaps priming it to fail at a specific point in the seasonal cycle. Furthermore, the immense internal heat bubbling up from the planet's interior provides the constant fuel for these events. The great white spots, therefore, are not random explosions but the inevitable result of a colossal, ongoing energy battle between the planet's internal furnace and the changing influence of external sunlight. A battle that periodically erupts into one of the most spectacular displays of meteorological power in our solar system. By studying this cycle, we are learning to read the vital signs of a gas giant, understanding how it breathes, churns, and periodically unleashes its inner fury for all the cosmos to see. This relentless cosmic drizzle, this cascade of ice we call ring rain, holds a deeper secret than just its mere existence. For decades, we imagined it as a simple shower of water ice, a straightforward transfer of frozen material from the rings to the planet. But when the Cassini spacecraft dared to fly through the narrow gap between the rings and Saturn's cloud tops during its final grand finale orbits, its instruments tasted this precipitation directly, and the flavor was far more complex and exotic than anyone had predicted. This wasn't just pure water snow. It was a rich chemical cocktail, a brew of complex organic molecules and strange, gritty particles that has forced scientists to completely rethink the nature of the rings themselves and their dynamic relationship with the giant planet. The first astonishing finding was the sheer variety of organic compounds mixed in with the water. Cassini's mass spectrometer detected molecules like methane, ammonia, carbon dioxide, and even more complex carbon-rich compounds. The presence of these materials is a game changer. It tells us that the rings are not simply made of sterile, pristine water ice. Instead, they are chemically complex, laced with the kind of building blocks that are fundamental to the chemistry of life. How did these organics get there? The most likely explanation points to constant micro-meteoroid bombardment. The rings are perpetually being sandblasted by tiny dust particles from the outer solar system. These impacts do more than just chip away at the ice. They deliver a constant rain of foreign, carbon-rich material and, more importantly, provide the energy for chemical reactions. When a micrometeoroid slams into a ring particle, the tremendous heat and pressure of the impact can literally cook new, more complex molecules out of the simple ices and the incoming dust, creating a layer of organic gunk on the surface of the ring particles. This material then gets electrically charged and swept up in the ring rain, delivering a sprinkle of probiotic chemistry directly into Saturn's upper atmosphere. But the real showstopper, the finding that truly left researchers stunned, was the discovery of nanosilicate particles. These are tiny, incredibly fine grains of rock, essentially minuscule specks of sand. Their detection was a genuine puzzle. The rings are overwhelmingly composed of water ice, which is very bright and reflective. Silicates or rocky material are dark and absorbent. If the rings contained a significant amount of these silicates, they would appear much darker to our telescopes than they actually do. So, where are these gritty particles coming from, and why don't we see their dark signature spread throughout the rings? The answer seems to lie in a process of segregation and focusing. The leading theory suggests that these silicates are indeed delivered by micrometeoroid impacts, just like the organics. However, because they are much denser and less volatile than ice, they behave differently once they are released. When an impact occurs, it vaporizes some ice and ejects both icy and rocky dust. The lighter, fluffier ice particles can easily become electrically charged and get picked up by Saturn's magnetic field to begin their journey down as ring rain. The tiny silicate grains, being denser, might also get charged and swept away, but they are not a major component of the bulk ring material. They are a trace contaminant, a subtle spice in the recipe that is efficiently and selectively scavenged by the magnetic field and funneled planetward. This selective process reveals an incredible dynamic. Saturn's magnetic field is not just a passive conduit. It's an active filter, a cosmic sorting mechanism that is constantly cleansing its rings. It appears to be preferentially siphoning off the tiny, charged impurities, the organics and the silicates, while leaving the larger, purer ice particles behind to continue their orbital dance. This could be a key reason why the rings appear so brilliantly white and pristine to us from a distance. The planet is continuously giving itself a chemical facial, using its own magnetic field to wash away the cosmic dirt and dust that constantly falls upon its rings. This ongoing purification process helps maintain the rings' youthful gleam and supports the theory that they are a relatively recent addition to the Saturnian system. If they were billions of years old, this relentless rain of dark material from micrometeoroids would have thoroughly darkened them by now despite this magnetic cleansing. The composition of the ring rain, therefore, is much more than a list of ingredients. It is a forensic tool, a sample that tells a story of external contamination and internal processing. The organic molecules speak to a history of constant bombardment and in situ chemistry happening right there in the rings, turning them into vast, flat laboratories for prebiotic reactions. The nanosilicates act as tracers, revealing the hidden hand of Saturn's magnetic field in sculpting and maintaining the ring's appearance. Together, they paint a picture of the rings as a far more dynamic and chemically active environment than we ever imagined. Not a static, frozen monument, but a living, breathing system in constant chemical exchange with the planet it orbits. This subtle drizzle, invisible to the human eye, carries within it the encoded history of the rings' interactions with the entire solar system, a history we are only just beginning to decode. As we move from the grand, atmospheric upheavals of the planet to its intricate ring system, we find that even the smallest members of Saturn's family are capable of producing staggering surprises. Hidden within the gaps of the rings themselves are two tiny moons whose appearance is so bizarre it seems to defy the conventional image of a rounded, cratered world. Meet Pan and Atlas, two of Saturn's innermost moons, which look less like celestial bodies and more like delicate, cosmic ravioli or perhaps oversized, walnut-shaped flying saucers. When the Cassini spacecraft returned its first close-up images of these objects, scientists were met with a sight that was both comical and deeply puzzling. A form that appears almost manufactured, with a bulging, razor-sharp ridge of material encircling their equators, making them some of the most unusually shaped objects we have ever discovered in our solar system. To understand how these strange forms came to be, we must first look at where they live. Pan, the innermost known moon of Saturn, orbits within the Enke Gap, a 325-kilometer wide clearing in the outer part of the ring. Atlas similarly patrols the outer edge of the ring, just beyond the brilliant main rings orbiting within the Roche division. These are not passive inhabitants of these regions, they are active shepherds. Their gravity is just strong enough to sweep their orbital paths clear of the smaller ring particles, carving out and maintaining these distinct gaps. As they travel along these cleared lanes, they are continuously bombarded by the fine dust and ice particles that make up the rings on either side of them. This is the key to their peculiar shape. They are cosmic snowplows, gathering a skirt of ring material as they move. The process that shapes them is a delicate balancing act of forces. Picture one of these small moons, perhaps only 20 miles across, orbiting within its gap. It has its own weak gravity, enough to attract the tiny, icy particles that surround it. However, because these moons are so close to Saturn, the planet's immense tidal forces are also at play. These tidal forces tend to pull objects apart, but for a small, cohesive moon, they create a preferred plane for accretion, the equatorial plane. As the moon travels through its gap, the fine ring particles it encounters are naturally drawn toward this zone of stability. Over millions of years, this results in a slow, steady accumulation of material that settles into a disk around the moon's middle. This isn't a haphazard collection of debris. The particles arrange themselves into a remarkably smooth and symmetrical ridge because any lump that tries to form outside this preferred plane is quickly pulled down by the Moon's own gravity or stripped away by Saturn's tides. The result is that distinctive, sharp-edged equatorial bulge that gives these moons their unforgettable ravioli-like profile. What makes the shapes of Pan and Atlas so extraordinary is the sheer prominence of their ridges. On Atlas, the equatorial ridge is so pronounced that the Moon's polar diameter is less than half its equatorial diameter, creating an incredibly flattened flying saucer appearance. This is not a subtle feature, it is the dominant aspect of their geology. The ridge itself appears to be composed of fine, bright, icy material, much like the surrounding rings, and its surface is incredibly smooth, suggesting that it is made of loose, unconsolidated powder that has settled gently over eons. This provides a stunningly clear snapshot of an accretion process in action. We are essentially witnessing the earliest stages of how small bodies can grow by gathering material from a circumstellar disk, a process that, on a much larger scale, built all the planets in our solar system. Pan and Atlas are living laboratories, demonstrating how a seed object can sweep up material from a flat disk and incorporate it into its own structure. Yet, this elegant explanation doesn't quite close the case. Several intriguing questions about these tiny worlds remain open, adding further layers to their mystery. For instance, why do Pan and Atlas have such well-defined ridges, while other ring moons like Daphne's show only a much fainter accumulation? The answer likely lies in the specific characteristics of their orbits and the density of the ring material they are plowing through. A moon orbiting in a denser part of the ring system would encounter more material and potentially build a larger ridge more quickly. Another puzzle is the long-term stability of these structures. The ridges are gravitationally bound, but they are also incredibly delicate. A significant collision with a larger fragment could potentially disrupt this carefully accumulated skirt, scattering it back into the rings. The fact that we see these structures at all suggests that the orbital environments within these gaps are remarkably stable, and that these moons have been peacefully gathering their icy skirts for a very long time. The existence of Pan and Atlas provides a breathtakingly clear view of the dynamic and ongoing processes of creation and decoration that are constantly at work within the brilliant, complex disk that crowns the solar system's most majestic planet. And while we have marveled at the lakes and rivers of liquid methane that carve Titan's surface, this very existence presents us with one of the moon's most fundamental and perplexing conundrums. The methane that fills those seas and falls as rain is not a permanent feature. It is a fragile molecule in a constant state of destruction. High in Titan's thick, hazy atmosphere, the feeble sunlight, though only 1% as strong as what we receive on Earth, carries enough ultraviolet energy to relentlessly break methane molecules apart. This photochemical dissociation rips the methane into its constituent atoms, which then recombine into more complex hydrocarbons like ethane and acetylene, and into the heavy, reddish organic gunk called tholins that gives Titan its orange shroud. This process is so efficient that scientists have calculated all the methane currently in Titan's atmosphere should have been completely depleted within a few tens of millions of years. Yet Titan is 4.5 billion years old. The methane is still there, falling as rain and pooling in lakes today. This means something somewhere must be continuously replenishing it. The methane mystery is therefore a question of planetary plumbing on a grand scale. Where is Titan hiding its enormous methane reserves, and what geological process is actively tapping into them to keep the entire hydrological cycle alive? The leading theory points the finger deep beneath the frozen surface, suggesting Titan may harbor vast subsurface reservoirs of liquid methane, perhaps mixed with ethane and nitrogen, forming a kind of underground aquifer system. This idea paints a picture of Titan not just as a world with surface lakes, but as a world with a global hydrocarbon table. In this scenario, the methane slowly seeps up from these buried reserves through cracks and porous ice, venting into the atmosphere to replace what is being destroyed by sunlight. This could happen gradually, like a slow, planet-wide leak, or in more localized, discrete events. The challenge with this theory is finding direct evidence for these reservoirs and understanding the mechanics of how the methane moves through the icy crust. Another compelling possibility is that Titan is an active world, geologically speaking, and that cryovolcanism is the delivery mechanism. Instead of spewing molten rock, a Titanian cryovolcano would erupt a chilly slurry of water, ammonia, ice, and liquid methane. These hypothetical volcanoes would act as direct methane pumps, drawing the liquid from a deep, subsurface ocean or from pockets within the ice shell and injecting it directly into the atmosphere. This would elegantly solve the resupply problem, but it demands that Titan have a significant internal heat source to power such activity. This search for a definitive geological smoking gun has proven incredibly difficult. Over the years, Cassini's radar and infrared instruments identified several candidate features that looked suspiciously like cryovolcanic domes or flows. One of the most prominent, a region called Sotra Patera, even has what appears to be a deep pit next to a large, rounded mountain, a formation that bears a striking resemblance to volcanic calderas on Earth. Yet, for every feature that suggests past or present activity, there is a counter-argument. The surface of Titan is also covered in vast fields of dunes made of dark, sand-like hydrocarbons, and many of the proposed volcanic flows could potentially be explained as other processes, like the oozing of a thick, organic sludge that isn't driven by internal heat. The most telling piece of evidence would be a clear, direct detection of a warm spot on the surface, an unambiguous thermal signature of recent eruption. While Cassini did detect some subtle temperature variations, it never found a blazingly hot cryovolcano. The evidence for widespread, ongoing cryovolcanism remains tantalizingly circumstantial rather than conclusive. We are left with a situation where the atmospheric chemistry screams that replenishment must be happening, but the geological trail has gone frustratingly cold, leaving us without a confirmed culprit. This enduring mystery forces scientists to consider even more exotic possibilities that stretch our understanding of planetary science. One fascinating hypothesis suggests that the methane might not be coming from inside Titan at all, but could instead be delivered from the outside by comet impacts. While occasional impacts certainly happen, they are considered far too infrequent to sustain the steady, continuous resupply needed to balance the relentless photochemical loss. The rate of destruction is simply too high for such a sporadic source to keep up. Another, more profound idea delves into Titan's deepest history. It is possible that the Moon formed with a massive primordial store of methane trapped within its structure, perhaps locked away in a strange, crystalline form of water ice called a clathrate hydrate that forms a stable cage around methane molecules. This methane clathrate layer could act as a vast global reservoir, slowly releasing its stored gas over billions of years through a process of gradual dissociation. The internal heat from radioactive decay in Titan's core, or the heat generated by the gravitational tug of war with Saturn, could be just enough to slowly melt these clathrate cages, allowing a steady trickle of methane to migrate upward and sustain the atmosphere. Resolving the methane mystery is about far more than just accounting for a gas on a distant moon. It cuts to the very heart of Titan's nature as a world. Is it a geologically active body with a warm interior and cryovolcanos, or is it a more passive world, slowly and steadily outgassing its ancient primordial inheritance? The answer will fundamentally shape our understanding of its potential for habitability. An active interior with a liquid water ocean in contact with a rocky core, is a far more promising environment for probiotic chemistry and possibly even life than a cold, geologically dead ice ball. The continuous cycling of methane, driven by some hidden internal or chemical engine, makes Titan one of the most dynamic and Earth-like worlds in the solar system despite its alien chemistry. Until we can send a new mission to land on its surface and peer beneath its icy shell, the source of Titan's methane will remain one of the most captivating unsolved puzzles, a reminder that even the most detailed observations can still leave us wondering about the secret workings of another world. But the elegant, sweeping arcs of Saturn's rings are not the work of chance alone. They are masterpieces of gravitational artistry, sculpted by a troupe of tiny, hidden choreographers. Venture into the thin, bright F-ring, a delicate band that orbits just beyond the main rings, and you will find two of these artists in action, Prometheus and Pandora. These are the shepherds, small, potato-shaped moons whose gravitational influence is so precise it carves and confines the ring material, creating some of the most sharply defined edges in the entire Saturnian system. Every time Prometheus, the inner shepherd, makes its slightly elliptical orbit, it dives closest to the F-ring. Its gravity reaches out and tugs at the tiny, icy particles, stealing a bit of their momentum and pulling them inward. This repeated, rhythmic plucking creates a beautiful, predictable pattern of channels and kinks in the ring, like a celestial potter gently dragging a finger through wet clay. On the other side, the outer moon Pandora exerts its own pull, herding any stray particles that try to drift outward back toward the center. Together, these two dancers perform a delicate gravitational ballet, one pushing and the other pulling, to keep the slender F-ring tightly confined, a feat of celestial precision that prevents it from either dissipating into space or collapsing inward. This phenomenon of gravitational shepherding is not limited to the F-ring. Throughout the ring system, small moons act as cosmic sculptors, their subtle influence creating an astonishing variety of structures. Some moons, like Daphne's orbiting within the Keeler Gap, create not just clean edges but spectacular ripples. As this tiny moon moves, its gravity perturbs the ring particles both above and below its orbital plane, lifting them in majestic, vertical waves that can tower a mile high, a mountain range of ice particles moving in perfect harmony. In other regions, moons that orbit just outside a ring can create spiral density waves, much like the spiral arms of a galaxy. As the moon and the ring particles interact gravitationally, they set up a wave pattern that propagates through the ring like a ripple across a pond, but wound into a tight spiral by the different orbital speeds of the particles. These waves are not just beautiful, they are scientific tools. By studying their exact spacing and form, planetary scientists can literally weigh the moons that created them and even probe the density and viscosity of the ring material itself, turning the rings into a vast natural physics laboratory. Yet, the very existence of these perfectly positioned shepherds presents a profound and chicken or egg-style mystery. How did these moons form in such exact orbital resonances with the rings, and are they the cause of the rings' sharp boundaries, or are they a consequence of them? The conventional formation story for moons around gas giants involves accretion within a protoplanetary disk, where dust and ice clump together to form larger bodies. But for a shepherd moon like Prometheus orbiting so close to the rings, this process is fraught with difficulty. The intense tidal forces from Saturn at that distance make it hard for material to coalesce. The same forces that would pull a larger moon apart also prevent a small one from easily forming. This leads to a compelling alternative theory. Perhaps these shepherds are the shattered remnants of a larger moon that met a violent end. A catastrophic collision could have blown a single, larger moon to pieces, with the fragments finding stable orbits that just happen to be in these precise resonant locations, their positions dictated by the physics of the breakup and the ensuing gravitational interactions. Another, even more intriguing possibility is that the shepherds are not ancient at all. but are relatively recent arrivals, constantly forming and reforming from the ring material itself. In this scenario, the rings are not passive, they are a fertile ground for the birth of new moons. Small, dense clumps within the rings could, through their own collective gravity, begin to gather more material, snowballing into a larger object right before our eyes. The sharp edges of gaps and rings could be the very nurseries where this happens. Once a small aggregate forms, its own gravity would begin to clear a gap around itself, enhancing its ability to grow by preventing new material from being scattered away. This process, known as accretion, could be ongoing, suggesting that the shepherding moons we see today might be temporary tenants, destined to eventually drift away or be torn apart by tides, only to be replaced by new moons born from the endless flow of ice. The fact that many of these moons have low densities and are highly porous supports this idea, as they would be exactly what you would expect from an object that formed by gently gathering loose, icy snow. The mystery of the shepherds, therefore, is a window into the dynamic and ever-changing nature of the entire Saturnian system. Their precise locations and delicate gravitational dance are what grant the rings their stunning clarity and complex architecture, proving that even the smallest actors can play a starring role in shaping a cosmic landscape. Whether they are ancient survivors of a catastrophic breakup or newborn worlds still emerging from the raw material of the rings, their continued presence is a testament to the intricate balance of forces, gravity, tides, and collision that governs this region of space. By studying these tiny celestial herders, we are not just understanding how Saturn's rings look today. We are glimpsing the fundamental processes of creation and destruction that have shaped and continue to reshape every disk of material, from the rings of a planet to the birthplaces of solar systems across the galaxy. Yet this dark material, which creates such a stark contrast on Iapetus, does not originate there. It is an alien substance, a cosmic import from a far more distant and ancient member of Saturn's family. To trace its source, we must journey outward past the brilliant rings and the inner icy moons to the dark, irregular world of Phoebe. This moon is an outsider in every sense. Unlike the spherical moons that formed in orbit around Saturn, Phoebe is a captured object, a wanderer from the distant Kuiper belt that was snared by the planet's gravity long ago. Its orbit is a testament to its foreign origins. It moves in a retrograde direction, backwards compared to nearly everything else in the system, and its path is tilted and eccentric. Its surface is one of the darkest in the solar system, reflecting only about 6% of the light that hits it, and it is heavily cratered, a battered relic from the solar system's violent infancy. Phoebe is essentially a massive, dark mountain of ice and rock coated in a layer of primordial soot. This sooty coating is the key to the entire mystery. Phoebe is constantly bombarded by micrometeoroids, and these impacts do not just create craters, they also blast fine, dark dust off its surface and into space. Because Phoebe orbits in the opposite direction to the flow of material in the inner system, this ejected dust finds itself moving against the grain. The pressure from sunlight and other forces then causes this cloud of particles to slowly spiral inward toward Saturn, creating a vast, tenuous, and nearly invisible ring that orbits the planet in retrograde. This is the Phoebe ring, a colossal torus of dust discovered by the Spitzer Space Telescope, so diffuse that it would be impossible to see with the naked eye, yet immense enough that it would stretch from the Earth to the Moon. Iapetus, with its inclined orbit, acts like a celestial windshield wiper, plowing directly through this ethereal river of dark dust. Because Iapetus is tidally locked, always showing the same face forward in its orbit, this leading hemisphere bears the full brunt of the bombardment, continuously collecting a thin film of the dark material like bugs splattering on a car's front grille. But the simple act of collection is only the beginning of the story. The real mystery lies in the specific chemical nature of this dark coating and the powerful feedback loop that amplified its effect to create such an extreme dichotomy. The material itself is not just simple dirt. Spectroscopic analysis reveals it to be a complex mixture of carbon-rich compounds, similar to the material found on certain asteroids and comets. These are complex organic molecules called tholins, which form when simple ices like methane and ammonia are exposed to ultraviolet radiation from the sun. This process, essentially a form of cosmic chemistry, creates a dark, reddish-brown tar-like substance. Phoebe, having spent eons in the deep freeze of the outer solar system, has a surface rich in these primordial, irradiated ices, making it a perfect factory for this dark organic dust. Once this dark dust begins to settle on Iapetus's leading hemisphere, it sets in motion a self-reinforcing thermal process that locks in the two-faced appearance. The initial dark coating makes that hemisphere slightly better at absorbing sunlight. As it absorbs more solar energy, it grows warmer. This is the crucial trigger. On the frigid surface of Iapetus, this slight warming is enough to cause a phenomenon called thermal sublimation. The clean, bright water ice on the darkened areas doesn't melt. It turns directly from a solid into a gas, skipping the liquid phase entirely. This water vapor then migrates across the moon's surface, eventually reaching the colder regions, the trailing hemisphere, and the poles where it condenses and refreezes, adding a fresh, brilliant layer of white frost. This creates a powerful feedback loop. As the dark areas lose their ice, they become even darker and absorb even more heat, which sublimates even more ice. Meanwhile, the bright areas gain more ice, making them even brighter and colder, further locking in the frost. Over millions of years, this process effectively engineered the moon's two extreme personalities, one sinking into a deep, dark warmth and the other ascending to a brilliant, frozen chill. The astonishing effectiveness of this process, however, raises its own perplexing questions. Why is the boundary between the light and dark regions so incredibly sharp in many places? The thermal segregation process would, in theory, tend to create a more gradual, blended transition, yet on Iapetus, the line between Cassini Reggio and the bright terrain is often knife-edge, changing over just a few dozen kilometers. This suggests that other, more complex geological or chemical processes might be at work, perhaps involving the specific way the dark material bonds to the ice or the influence of the moon's own weak gravity in focusing the movement of the water vapor. Furthermore, the global-scale coordination of the pattern is a marvel of its own, a perfect alignment with the orbital motion that speaks to the powerful and consistent nature of the forces that shaped it. The dark material of Iapetus and Phoebe is more than just a stain. It is the active ingredient in a planetary-scale alchemical reaction, a sprinkling of foreign dust that, through the relentless and predictable workings of physics, transformed an entire world into a celestial masterpiece of light and shadow. Yet, for all the visible wonders of Saturn's atmosphere and rings, some of its most profound secrets are completely invisible, hidden deep within the planet's churning heart. To uncover them, we had to send a robotic explorer on a final, suicidal mission. During its grand finale, the Cassini spacecraft performed 22 daring dives through the narrow gap between Saturn and its innermost rings. This was not just a spectacular finale, it was an unparalleled scientific opportunity. By tracking the tiny fluctuations in Cassini's radio signal as it sped past the planet at over 70,000 miles per hour, scientists could measure the subtle tug of Saturn's gravity with exquisite precision. They expected to map a relatively simple, layered world with mass distributed in smooth, concentric shells. What they found was far more bizarre and revealing. Saturn's gravity is lopsided. The gravitational pull is not the same in the northern and southern hemispheres, and this asymmetry is baked deep into the planet's fluid interior, forcing a complete rethinking of what happens inside a gas giant. This discovery of a gravitational imbalance was a genuine shock. For a planet like Earth with a solid surface and mountain ranges, small gravitational anomalies are expected. But for a gas giant like Saturn, which is essentially a massive, swirling ball of fluid, the rapid rotation should smooth everything out, creating a gravitational field that is almost perfectly symmetrical about its spin axis. The fact that it isn't tells us that the flow of material deep within Saturn is not uniform or orderly. Instead, there are massive, asymmetric currents of material circulating at incredible depths, creating regions of slightly higher and lower density that exert a measurably different gravitational pull. Imagine a perfectly smooth, spinning ball of dough. Now, imagine embedding a few large, dense chunks of fruit randomly inside it. As the ball spins, its wobble would be slightly off-center. Cassini's measurements effectively detected Saturn's wobble, revealing the hidden fruit within its vast, gaseous dough. So, what could cause these deep-seated asymmetries? The leading theory points the finger at the planet's ferocious jet streams. Saturn is banded with east-west winds that can reach speeds of over 1,000 miles per hour. For decades, planetary scientists debated whether these dazzling cloud-level jets were just shallow weather phenomena like Earth's jet streams, or whether they were surface manifestations of much deeper planet-wide circulation. The lopsided gravity data strongly supports the deep flow model. It suggests that these jet streams extend thousands of miles down into the planet's interior, all the way to a layer where the pressure is so immense that hydrogen behaves like a liquid metal. These deep rivers of fluid flowing at different latitudes and speeds carry mass with them. A jet stream moving slightly faster in the northern hemisphere could be transporting a colossal amount of material, creating a persistent planet-scale density anomaly that Cassini could detect from its delicate orbital dance. This revelation fundamentally challenges the classic onion model of planetary interiors, where a planet is visualized as a set of neat, uniform layers, a gaseous outer envelope, a layer of liquid metallic hydrogen, and a central rocky core. Saturn's interior is not a set of calm, still layers. It is a vigorously active, dynamic engine. The deep flows imply a constant transport of heat and material from the interior outward, a churning that likely influences everything from the planet's mysterious excess heat to the stability of its colossal storms. Furthermore, the persistence of these asymmetries over time suggests that the internal structure of the core itself might be more complex than a simple, solid ball of rock and ice. Some models now propose that Saturn's core might not be a distinct, compact object at all, but rather a diffuse, fuzzy region of heavier elements gradually dissolving into the surrounding envelope of liquid metallic hydrogen, a structure that would naturally allow for more complex and lopsided internal flows. Understanding this lopsided gravity is not just about solving a puzzle for Saturn. It reshapes our entire conception of how gas giants work. It provides the first direct evidence that the spectacular weather we see in the cloud tops is fundamentally linked to motions occurring thousands of miles below, in a realm of exotic matter and crushing pressures that we can never directly visit. The invisible hand of these deep flows likely sculpts the planet's magnetic field, drives its heat distribution, and contributes to the bizarre stability of features like the North Polar hexagon. By daring to fly where no spacecraft had gone before, Cassini gave us a gravitational X-ray vision into Saturn's soul, revealing a world that is not a serene, layered sphere, but a violently churning, lopsided, and profoundly dynamic giant, whose inner turmoil is written invisibly in the fabric of space itself. Even among the dynamic wonders of the Saturnian system, few celestial bodies present as clean and youthful a face as the small, gleaming moon Enceladus. Its surface is a landscape of profound paradox, a frozen crust that appears as fresh and unblemished as a sheet of ice newly formed on a winter pond. When planetary scientists first saw high-resolution images from the Cassini spacecraft, they were struck not by the craters that typically record billions of years of cosmic bombardment, but by their near-total absence. Vast regions of Enceladus are covered in smooth, plains of brilliant white ice, crisscrossed by deep, bluish fractures that look as though they were carved only yesterday. This is a world that has been resurfaced, its ancient scars erased and filled in with new, pristine ice, an ongoing process that leaves its face remarkably young. The scarcity of impact craters allows scientists to date different surfaces, and the calculations point to a staggering conclusion. Some areas of Enceladus may be less than 100 million years old, and in geological terms, that is the equivalent of a surface that was repaved just last week. This perpetual youth presents a fundamental thermodynamic puzzle, demanding an explanation for the immense and continuous energy required to power such geological rebirth on a world so small and so distant from the sun's warmth. The engine for this global facelift is the spectacular cryovolcanism at its south pole, the towering geysers that blast water vapor and ice crystals into space from the infamous tiger stripe fractures. But powering these immense, continuous plumes requires a prodigious and sustained source of heat, far more than this 500-kilometer-wide moon should theoretically possess. The leading explanation for decades has been tidal heating, a process where the gravitational pull of Saturn and the larger moon Dione flex and squeeze Enceladus's interior. As its orbit becomes slightly elliptical, the moon is subjected to a rhythmic deformation, stretching and compressing its rocky core and icy shell. This internal friction generates heat, much like repeatedly bending a metal coat hanger back and forth will make it warm to the touch. For a small moon like Enceladus, however, the mathematics of this process have always been challenging. The tidal forces exerted by Saturn, while immense, should not be sufficient on their own to generate the level of observed activity, especially to maintain a global subsurface ocean in a liquid state and drive such violent eruptions for billions of years. The energy budget simply doesn't balance. The moon should have frozen solid eons ago. This discrepancy points toward a more complex and dynamic internal structure than a simple ball of ice and rock. The emerging picture of Enceladus's interior is one of a highly differentiated and potentially stratified world. Scientists now suspect that its rocky core is not a single, solid lump, but rather a porous, fragmented, or even a rubble pile structure, more like a collection of boulders with water percolating through the gaps than a monolithic sphere. This configuration is crucial because it dramatically increases the surface area where liquid water can interact with rock. Tidal forces flexing this porous, water-logged core would generate far more heat through friction than they would against a smooth, solid core. Furthermore, this water-rock interaction at elevated temperatures is a recipe for serpentinization, a chemical reaction that releases substantial additional heat as a byproduct. This transforms the core from a passive heat sink into an active, chemically powered radiator, potentially providing the extra energy needed to sustain the moon's ocean and geological activity over long periods. The mystery of the moon's enduring energy supply also forces a re-examination of its orbital history. Enceladus may not have always been as active as it is today. Its history could be one of dramatic episodic outbursts rather than a constant, steady simmer. The moon's orbit is locked in a 2-to-1 resonance with Dione, meaning for every 2 orbits Enceladus completes, Dione completes 1. This gravitational partnership keeps Enceladus's orbit slightly eccentric, which is the key driver of tidal heating. But orbital resonances can change over time. It is possible that in the past, Enceladus experienced periods of even greater orbital eccentricity, perhaps triggered by a close gravitational encounter with another moon or a shift in the overall satellite system. During these hot phases, the tidal heating would have been far more intense, leading to massive resurfacing events that erased nearly all existing craters. The moon we see today could be in a relatively quieter phase, but one still powered by the heat trapped from a more violent and dynamic past. Alternatively, the system may be self-regulating, The heat generated within Enceladus can actually affect its own orbit, creating a feedback loop that prevents the Moon from ever completely freezing or overheating, locking it into a stable, long-term cycle of activity. The youthful appearance of Enceladus is therefore far more than a surface curiosity. It is a direct window into the Moon's hidden, churning heart and its intricate gravitational dance with its neighbors. It challenges our basic assumptions about the thermal evolution of small icy worlds and suggests that they can harbor immense, long-lived energy sources through a combination of orbital mechanics and sophisticated internal chemistry. This sustained activity is what makes Enceladus such a compelling candidate for habitability, as it ensures that its subsurface ocean has remained a liquid water environment, potentially for billions of years, offering a stable sanctuary where life's delicate chemistry could have taken root and endured. The unblemished ice we see is the outer expression of a powerful, living interior, a frozen crust hiding a warm, salty, and potentially life-giving sea. As we turn from the dramatic geysers of Enceladus to the vast magnetic environment of Saturn, we uncover a connection so intimate and energetic it links the two worlds with an invisible high-voltage tether. The Cassini spacecraft didn't just observe the Moon and the planet separately. It detected a continuous, flowing river of electricity between them, a powerful circuit that transforms Enceladus from a passive orb into an active component in Saturn's electromagnetic system. The story of this discovery begins with the plumes themselves. Every second, Enceladus erupts, sending vast quantities of water vapor and ice crystals into the vacuum of space. But in this airless void, the particles are bombarded by ultraviolet light from the Sun and slammed by energetic particles trapped in Saturn's magnetic field. This violent process strips electrons from the water molecules, creating a cloud of electrically charged gas or plasma. This ionized plume is no longer just water. It becomes a conductive soup of positively charged ions and free-flying electrons, and it is this electrified material that gets caught in the cosmic current. Saturn's magnetic field acts as the wires for this immense circuit. The field lines, which normally sweep through space in graceful arcs, are forced to slice directly through the plume of Enceladus. As the Moon orbits, its erupting material loads these magnetic field lines with fresh, ionized particles. The physics of magnetized plasma then takes over, and these loaded field lines are compelled to slide, creating a phenomenon known as field line dragging. This motion of conductive plasma across magnetic field lines is a perfect recipe for generating an electric current. Think of it like a celestial generator. The Moon's geysers provide the conductive fluid, and its orbital motion through Saturn's magnetic field provides the dynamo effect. This sets up a flow of electricity, a circuit where electrons stream one way and ions flow the other, creating a closed loop that runs from the plume of Enceladus down the magnetic field lines and directly into the upper atmosphere of Saturn near its north and south poles. The most stunning visual proof of this circuit is not at Enceladus but at Saturn. Just as charged particles following magnetic field lines create the glowing auroras on Earth, the electrons streaming from Enceladus along this cosmic wire slam into the hydrogen gas of Saturn's upper atmosphere. When they collide, they transfer their energy, causing the gas to glow with a faint, ultraviolet light. Cassini's instruments detected this specific, isolated patch of auroral light, a distinct and unusually small spot of shimmering energy fixed in Saturn's polar sky. This wasn't a large, dancing curtain of light like the main auroras. It was a focused beacon, a direct footprint of the electrical connection to Enceladus. Pinpointing this spot allowed scientists to measure the power of the circuit, and the numbers are staggering. The current flowing between the two bodies is estimated to be around 100,000 amps, a flow of electricity powerful enough to supply a small city. This makes the tiny Moon a significant player in energizing the local space environment around Saturn. Yet the full scale and impact of this interaction remain an active and compelling mystery. Scientists are still working to understand the complete pathway of this energy and how it dissipates. Does the circuit flow smoothly, or does it encounter resistance and create sparks and turbulence within the plasma? Furthermore, this process is not just a one-way street of energy from Saturn to its moon. Enceladus is actively feeding material and charge back into the planet's system, effectively polluting Saturn's magnetosphere with its water-based plasma. This constant injection of fresh, heavy ions from the moon fundamentally changes the composition and behavior of the charged particles trapped in Saturn's magnetic field, influencing everything from the intensity of radio emissions to the structure of the vast, donut-shaped plasma torus that now encircles the planet, a torus that was built and is continuously replenished by the geysers. Enceladus, this tiny, active moon, is therefore not just a geological wonder. It is an astronomical electrical generator and a chemical factory whose output directly shapes the very space environment of the solar system's most majestic ringed world. Just as we've grappled with the question of where Titan's methane comes from, we stumble upon a related chemical puzzle that is equally baffling. If methane in the atmosphere is constantly being broken apart by sunlight, the fragments should naturally recombine to form more complex hydrocarbons, and the primary product of this cosmic chemistry should be ethane. In fact, based on the billions of years Titan has existed, scientists calculated that this process should have produced a layer of liquid ethane hundreds of meters thick, covering the entire moon. The expectation was that Titan's lakes and seas would be dominated by ethane, with methane merely a minor ingredient. Yet, when the Cassini spacecraft analyzed the composition of these lakes, the data revealed a startling contradiction. The dark, smooth surfaces of lakes like Kraken Mare are not ethane-rich. They are composed of remarkably pure methane. It's as if we found a vast ocean on Earth that was filled with pure hydrogen peroxide instead of salt water. This discovery of the missing ethane forces us to ask what happened to it all, and in doing so, it reveals that our understanding of Titan's surface and subsurface is still in its infancy. One of the most compelling theories to explain this absence suggests that the ethane hasn't vanished. It has simply seeped away out of sight. Titan's crust is thought to be a thick, frozen shell of water ice, but that ice may not be a solid, impermeable barrier. It could be incredibly porous, fractured, and cavernous, more like a celestial sponge than a solid floor. In this scenario, the ethane produced in the atmosphere rains down and, upon reaching the surface, does not simply pool in the lakes. Instead, it percolates downward, trickling through cracks and pores in the icy crust to fill a vast subsurface aquifer. This hidden reservoir could be truly immense, potentially holding far more liquid hydrocarbons than all the surface lakes and seas combined. Titan, in this view, would possess a global hydrocarbon table with liquid ethane and methane saturating its icy bedrock. The purer methane we see on the surface, then, could simply be the most volatile and mobile fraction of this much larger underground system, a lightweight layer that easily evaporates to sustain the atmospheric cycle while the heavier ethane remains trapped below. Another fascinating possibility involves a change of state, where the ethane is literally locked away in a solid form. In the extreme cold of Titan's surface, which hovers around -290 degrees Fahrenheit, ethane can behave in surprising ways. When mixed with other hydrocarbons or dissolved in methane, it can remain a liquid, but under the right conditions, it can precipitate out to form solid crystals, similar to how salt crystallizes from seawater. Some researchers propose that Titan's lakes could be undergoing a slow process of fractionation, where the ethane gradually settles out of the liquid methane as a fine silt, accumulating as a thick, muddy sludge on the lake bottoms. This ethane-rich gunk would be invisible to Cassini's radar, which only skimmed the liquid surface. Alternatively, the ethane could be reacting with the water ice bedrock itself. At these frigid temperatures, ethane can form stable, solid clathrate hydrates cage-like structures of water ice that trap hydrocarbon molecules inside them. This process would effectively armor the ethane, removing it from the active surface inventory and sequestering it within the very fabric of the Moon's crust. The mystery is further deepened by Titan's complex and varied geology. The Moon is not a uniform world. It has vast dun fields, mountainous regions, and plains of different compositions. It's possible that the missing ethane is not missing uniformly. Perhaps it has pooled in specific geological basins we have not yet observed in detail, or maybe it is concentrated in the vast, empty-looking equatorial deserts, soaked into the sand like organic grains that make up the dunes. The Huygens probe, which landed on a dry, pebble-strewn plain, detected evidence of methane dampness just below the surface, hinting at a complex subsurface hydrology that we have only barely sampled. Cassini's radar could only provide a broad overview, and without a dedicated mission to drill or conduct extensive seismic surveys, the true distribution of ethane across Titan's diverse landscape remains a major unknown. The Moon's seasonal cycles add yet another layer of complexity. As the long Titonian years progress, the distribution of liquids and the chemical reactions on the surface may shift dramatically, potentially hiding and revealing different hydrocarbon reservoirs over time. Ultimately, the case of the missing ethane is a powerful reminder that Titan is a world of active and interconnected chemical cycles, a system far more intricate than a simple one-way street from atmosphere to surface lake. The purity of the methane in its lakes suggests a continuous and efficient sorting mechanism is at work, one that preferentially keeps methane in the active weather cycle while diverting its chemical offspring into hidden sinks, whether they be underground aquifers, solid clathrate cages, or deep sedimentary basins. Solving this puzzle is critical because the distribution of these hydrocarbons speaks directly to Titan's geological activity and its potential for probiotic chemistry. A world with a deep, liquid hydrocarbon aquifer interacting with a warm, water-based ocean could be a far more interesting chemical factory than a world with only shallow surface puddles. The missing ethane is not just an accounting error. It is a clue pointing toward a hidden, dynamic, and still largely unexplored dimension of this alien world, a dimension we must understand if we are to ever fully unravel the secrets of our solar system's most Earth-like alien landscape. And as we marvel at the gravitational ballet of the shepherd moon sculpting the rings, we step back to witness an even grander and more intricate dance unfolding across the entire Saturnian system, a symphony of motion governed by the precise mathematics of orbital resonance. Imagine two moons racing around Saturn, one on a short, tight track close to the planet, the other on a long, looping path farther out. Now imagine that for every single orbit the outer moon completes, the inner moon completes exactly two. This is not a coincidence. It is a gravitational lockstep, a stable and self-reinforcing relationship known as a mean motion resonance. The moon's orbital periods form a simple, perfect ratio, like two notes in a chord that harmonize across the void. This phenomenon is not rare around Saturn. It is the rule, creating a web of interconnected rhythms that choreograph the motions of dozens of moons and fundamentally shape their very existence. One of the most striking examples is the relationship between Mimas and Tethys. Mimas, the moon famously resembling the Death Star, orbits closer to Saturn with a period of about 22 hours. Tethys, larger and more distant, takes roughly 45 hours to complete its journey. The ratio is 1:2. Tethys completes one orbit for every 2 orbits of Mimas. This lockstep creates a repeating gravitational conversation. Every time Mimas laps Tethys, which happens at the same point in their orbits, it gives Tethys a consistent, gentle gravitational tug. Over millions of years, these repeated, rhythmic tugs have acted to stabilize their orbits, preventing them from drifting into chaos. The resonance has even left a physical mark on the system. Tethys travels with two smaller Trojan moons, Tellisto and Calypso, which orbit 60 degrees ahead of and behind it in its path, trapped in the stable gravitational points created by its resonance with Saturn. This entire configuration is a celestial clockwork, a testament to the long-term ordering power of gravity. Perhaps the most consequential resonance, however, is the one that powers the most promising world for life in the outer solar system, the 2-to-1 resonance between Enceladus and the larger moon Dione. For every 2 orbits Enceladus makes around Saturn, Dione makes exactly 1. This partnership is the engine behind Enceladus's spectacular geological activity. Because of this resonance, Enceladus's orbit cannot become perfectly circular. The persistent gravitational nudges from Dione force it into a slight elliptical or oval-shaped path. This subtle eccentricity is everything. As Enceladus travels this elliptical orbit, its distance from Saturn constantly changes. When it is closer, Saturn's immense gravity squeezes it more strongly. When it is farther away, the grip relaxes. This perpetual rhythmic flexing, a process called tidal heating, generates immense friction deep within the moon's core. This internal heat is what keeps Enceladus's global subsurface ocean from freezing solid and provides the energy to drive the colossal water plumes erupting from its south pole. Without this resonant partnership with Dione, Enceladus would likely be a frozen, geologically dead ball of ice, its hidden ocean and all its potential for life locked away forever in the deep freeze. But how did this complex gravitational symphony become established in the first place? This is a central mystery that takes us back to the earliest, most chaotic days of the Saturnian system. The prevailing theory suggests that these resonances are not primordial. The moons did not form in these perfect ratios. Instead, they likely formed farther from Saturn and have been migrating outward over billions of years. The mechanism for this migration is a subtle but constant gravitational interaction with the planet itself. As a moon orbits, its gravitational pull creates a tidal bulge on Saturn. Because Saturn rotates faster than the moon orbits, this bulge is dragged slightly ahead of the moon. The gravity of this leading bulge then pulls the moon forward, giving it a tiny push that transfers energy and causes its orbit to slowly expand. This process, known as tidal migration, acts like a cosmic conveyor belt, gently moving moons outward over eons. The resonances lock in when the orbital periods of 2 migrating moons naturally approach a simple integer ratio. As an inner moon migrating outward catches up to the location where its period is exactly half that of an outer moon, their gravitational influences synchronize. Once this lock is achieved, it becomes incredibly stable. The moons continue to migrate, but they do so together, maintaining their perfect ratio like 2 gears in a machine that are moving as one. This process can also lead to dramatic chain reactions. The outward migration of a massive moon like Titan could have shaken the entire satellite system, scattering smaller moons and forcing them into new resonant relationships as they found stable niches in its gravitational wake. The intricate web we see today is likely the fossilized record of this great planetary migration, a dynamic history frozen into the precise mathematical relationships we can observe from Earth. Yet, for all its stabilizing beauty, this resonant dance also holds the seeds of potential instability and profound geological change. The tidal heating generated by these resonances doesn't just create geysers, it fundamentally alters the thermal and geological evolution of the moons involved. For Mimas, its resonance with Tethys generates some tidal friction, but apparently not enough to melt its interior, as it remains a heavily cratered, frozen world. The mystery is why Mimas is frozen while Enceladus is so spectacularly active when both are locked in similar 2-to-1 resonances. The answer likely lies in the composition and internal structure of the moons themselves. Enceladus may have a more porous, fragmented core that generates more heat through friction, or it might contain antifreeze compounds like ammonia that lower the melting point of its internal ocean. The same resonant gravitational push can therefore have wildly different consequences, depending on the unique character of the world feeling the strain. The long-term stability of this complex network is another open question. While resonances are stable over millions of years, they are not necessarily permanent. The system is a delicately balanced gravitational ecosystem. A close encounter with a passing comet or the slow, relentless outward migration of a major moon like Titan could potentially destabilize a key resonance. If the Enceladus-Dione resonance were to be broken, the geological consequences for Enceladus would be catastrophic. Its orbit would gradually circularize, the tidal heating would cease, and within a relatively short astronomical time frame, its geysers would fall silent, its ocean would freeze solid, and its bright, youthful surface would slowly darken under a relentless rain of cosmic dust. The resonant ballet of Saturn's moons is therefore a dynamic and ongoing performance, not a static display. It is a living system that has shaped the past, governs the present, and holds the key to the future evolution of these enigmatic worlds, proving that even in the silent vacuum of space, gravity composes a music that constantly shapes the worlds it holds in its sway. Just as the rings are a temporary spectacle, the planet itself harbors a deep and enduring power source that has long confounded scientists. If you could hold a cosmic energy meter up to Saturn, you would make a startling discovery. The giant planet radiates more than twice the amount of energy it absorbs from the distant sun. This is a profound violation of simple expectation for a world so far out in the cold depths of the solar system. After all, Jupiter, which is larger and closer to the Sun, emits roughly the same amount of excess heat. But Saturn, somehow, manages to be far hotter on the inside than it has any right to be based on solar heating alone. This tremendous outflow of energy is the fuel that drives its ferocious weather, its supersonic jet streams, and its colossal storms. Unraveling the source of this internal furnace is not just about accounting for a planetary power bill. It's about understanding the very life cycle and inner workings of a gas giant. The leading theory for this immense heat is a process as beautiful as it is violent, occurring in the planet's deepest layers where conditions defy earthly imagination. This theory centers on the idea of helium rain. To understand it, we must venture into a realm of crushing pressure and exotic matter. Deep within Saturn, the hydrogen that makes up most of the planet is compressed with such incredible force that it undergoes a phase transition, becoming a liquid metal. In this strange, electrically conductive sea, helium exists as a dissolved gas, much like carbon dioxide is dissolved in a bottle of soda. However, at these extreme pressures, helium is not particularly soluble in liquid metallic hydrogen. As the entire planet slowly cools over billions of years from its initial hot formation, it reaches a critical temperature threshold. At this point, the helium can no longer remain dissolved. It begins to condense into liquid droplets, much like water vapor condensing into rain in Earth's atmosphere. But this is no gentle shower. In the intense gravity of Saturn's interior, these newly formed droplets of liquid helium are significantly denser than the surrounding liquid metallic hydrogen. They begin to fall. This is not a fall of a few miles, but a descent of thousands upon thousands of kilometers toward the planet's center. As these countless trillions of helium droplets plummet inward, they lose gravitational potential energy. This energy does not simply vanish. It is converted into heat through friction, powerfully warming the surrounding hydrogen soup. This continuous, planet-wide drizzle of helium acts like a built-in gravitational engine, converting the separation of its internal constituents into raw thermal power. It's a slow-motion rearrangement of the planet's interior that has been releasing heat for billions of years, supplementing the leftover warmth from Saturn's violent formation. However, for all its elegance, the helium rain model is not a perfect solution. Sophisticated computer simulations of this process consistently indicate that it cannot, by itself, fully account for the sheer magnitude of Saturn's observed heat flow. The numbers simply don't add up. The predicted heat from helium rain plus the residual heat of formation still leaves a significant energy gap that remains unexplained. This forces planetary scientists to consider other, more exotic mechanisms that could be cooking the planet from the inside out. One compelling possibility involves the very core of Saturn itself. The traditional view of a compact, solid ball of rock and ice is being challenged by new data, including the puzzling lopsidedness of Saturn's gravity field. Some models now suggest the core might be a diffuse, fuzzy region where heavier elements are slowly dissolving and mixing into the envelope of liquid metallic hydrogen above it. This dissolution process would release a tremendous amount of gravitational energy as the dense core material sinks and stirs the lighter hydrogen, providing another potent and long-lasting source of internal heat. Another fascinating line of inquiry points to physical separation on an even grander scale. Beyond just helium separating from hydrogen, it's possible that other elements like neon or carbon are also undergoing similar processes of condensation and rainfall deep within the planet. Each of these differentiation events would contribute its own burst of gravitational heating, collectively adding up to a significant fraction of the missing energy. Furthermore, the churning, convective motions within the liquid metallic hydrogen layer itself generate heat through friction, a process that could be far more vigorous than our current models assume, especially if the interior is layered with complex compositions and phase boundaries that disrupt smooth flow. These additional sources are not mutually exclusive. The true answer likely lies in a combination of all these processes: helium rain, core erosion, multi-element separation, and vigorous convection working in concert to create the powerful thermal engine we observe. The mystery of Saturn's internal heat is therefore a classic scientific detective story where the prime suspect, helium rain, is almost certainly guilty, but it did not act alone. The full explanation requires a deeper understanding of the complex, dynamic, and still largely hidden chemistry and physics at work in the heart of the giant. After exploring the deep interior of the planet and the grand gravitational ballet of its moons, we now turn our attention to a feature so delicate and close to Saturn that it was one of the last to be discovered, a ring that proves even the faintest structures can hold monumental secrets. Lying closest to the planet's cloud tops, nestled between the brilliant sea ring and the planet's own hazy upper atmosphere, is the ethereal and ever-changing D-ring. It is the innermost of Saturn's rings, a whisper-thin band of dust so tenuous that for a long time, astronomers debated whether it was even real. While its more famous siblings, the A, B, and C rings, gleam with icy brilliance, the D ring is a ghost, a pale smudge of the finest particles. Yet within this faint and seemingly placid band, the Cassini spacecraft uncovered one of the most dynamic and precisely dated events in the entire solar system, a cosmic shockwave frozen in time. The key discovery was a series of subtle, spiral patterns, like the ripples from a stone dropped into a still pond, but on a scale that defies earthly comprehension. These corrugations, stretching across the entire D-ring, are not stationary. They are a continuous, tightly wound spiral, a frozen wave propagating through the ring particles. When scientists first analyzed the pattern, they realized they were looking at the aftermath of a specific, violent event. The spiral was not a permanent feature. Its exact geometry acted as a cosmic clock. By measuring the ever-so-slight tilt of the spiral pattern and understanding how such a wave would wind itself tighter over time due to Saturn's gravity, researchers could rewind the tape all the way back to its point of origin. The calculation pointed to a single, precise moment in 1984. This was not an arbitrary date. It was the year a known comet, likely a fragmented object from the Creutzfeldt-Sungrazer family, was predicted to have crossed Saturn's orbital plane. The conclusion was inescapable. A cloud of cometary debris, the scattered remains of this shattered ice ball, had slammed directly through the D-ring, tilting it and setting off a ripple that has been slowly winding itself tighter ever since. This ability to precisely date a celestial event from millions of miles away and decades after it occurred is a breathtaking demonstration of forensic astronomy. The ripples in the D-ring are more than just a beautiful pattern, they are a high-precision seismograph for the ring system. The initial impact imparted a gentle vertical velocity to the ring particles, essentially lifting a section of the ring and letting it settle back down, creating a wave that travels outward. The wavelength of this spiral is exquisitely sensitive to time, allowing scientists to pinpoint the impact event to within just a few months. Furthermore, by studying how the wave has propagated and dampened over the years, researchers can infer fundamental properties of the ring itself, such as the surface density of the particles and the forces of viscosity and collision that act between them. It's as if the comet's impact provided a controlled experiment, a single strike that allowed us to measure the physical properties of this faint ring in a way that would otherwise be impossible. Yet, for all we have learned from this dated cataclysm, the D-ring is far from a simple one-note mystery. It is a realm of transient and bizarre features that come and go, their origins still shrouded in uncertainty. Cassini's long-term observations revealed bright, narrow strands within the ring that would mysteriously appear, brighten, and then fade away over periods of just a few years. Some of these features appear to be braided or twisted, while others look like isolated clumps of material that defy the normal shepherding forces that govern ring structure. One of the most peculiar was a feature nicknamed D68, a sharp, bright ringlet that was observed to be slowly moving inward toward the planet at a rate of about 180 miles per year, a slow-motion drift that has no simple explanation. The forces at play in this inner sanctum are complex and poorly understood. The planet's own magnetic field is exceptionally strong here, and its gravity creates powerful tides that could be stirring the fine dust, causing it to clump and disperse in unpredictable ways. Some theories suggest these transient strands could be the result of recent, smaller impacts from meteoroid swarms, while others point to electromagnetic effects, where fine dust becomes charged and is then manipulated by Saturn's magnetic field like iron filings near a magnet. The enduring lesson of the D-ring is that Saturn's ring system is not a static museum piece. It is a living, breathing, and constantly evolving environment. The dramatic ripple from a 1984 comet impact shows us that the rings preserve a detailed history of their interactions with the solar system at large, recording cosmic events with the fidelity of a geological stratum. At the same time, the fleeting, unexplained strands and clumps demonstrate that there are active processes occurring right now that we do not fully comprehend, a subtle, ongoing dynamism in the planet's closest orbital neighborhood. This faint inner ring, once thought to be a simple curiosity, has revealed itself to be a sensitive and complex system, reacting to both internal and external forces, a place where the past is written in spirals and the present is a canvas for transient, mysterious art. And so, after 13 years of breathtaking discovery, the mission that had rewritten our understanding of the Saturnian system prepared for its final, most daring act. With its fuel nearly exhausted, the Cassini spacecraft was commanded not to drift silently into the void, but to plunge directly into the atmosphere of the planet it had studied for so long. This was the grand finale, a deliberate, heroic sacrifice designed to protect the pristine moons Enceladus and Titan from any possible contamination by earthly microbes that might have hitched a ride on the spacecraft. But this was far more than a controlled crash. It was a final, unprecedented experiment. For its last moments, Cassini transformed from a distant observer into an in-situ probe, diving into realms no human-made object had ever visited. Its instruments pointed forward, gathering a stream of data until its signal was finally consumed by the fire of atmospheric entry. The mystery we are left with is not what destroyed Cassini, but what its final, fragmentary whispers are telling us about the hidden nature of Saturn itself. During those last, breathtaking orbits, Cassini skimmed the upper fringes of Saturn's atmosphere, a region we had only ever observed from afar. Its suite of instruments worked furiously, acting as our senses in an alien environment. The mass spectrometer tasted the thin, outer air, analyzing its chemical makeup with precision. The magnetometer mapped the strength and orientation of the planet's magnetic field from an incredibly close range. Most critically, the radioscience experiment performed one last vital task. By precisely tracking the tiny wobbles and decelerations in Cassini's signal as it was buffeted by the tenuous atmospheric gases, scientists could measure the planet's gravitational field with a fidelity never before possible. This was akin to taking a fingerprint of Saturn's deep interior, as the subtle tugs on the spacecraft revealed the distribution of mass all the way down to the planet's core. The data it sent back in real time was a treasure trove, a final gift collected at the cost of its own existence. The full analysis of this unique dataset is a monumental task that continues to this day, a slow and painstaking process of decoding. Imagine trying to understand the entire blueprint of a colossal, churning machine by feeling the vibrations it transmits through a single, fleeting touch. Cassini's final moments provide that touch. The initial findings have already appended old models, such as confirming the startling lopsidedness of Saturn's gravity and revealing the deep flowing jet streams. But the deeper secrets are still emerging from the noise. The precise composition of the upper atmosphere, for instance, holds clues to the rate of ring rain and the nature of the material being deposited from the rings. A slight overabundance of certain molecules could tell us exactly how much water and organic dust is currently showering down from the rings, helping to refine our estimates of their remaining lifespan. Furthermore, the magnetic field data collected just seconds before loss of signal is crucial for solving the long-standing puzzle of Saturn's rotation. While the gravity measurements gave us a number for the length of a day, the final, ultra-close magnetic readings are being scrutinized for any tiny, periodic wobble that might have been masked at greater distances. Finding such a signal would provide a second, independent confirmation of the planetary spin, finally nailing down a fundamental property that eluded us for centuries. Moreover, the way the magnetic field interacted with the upper atmosphere during the plunge is teaching us about a region where the planet's internal magnetic dynamo meets the ionized outer layers of its gaseous envelope, a complex interface that is key to understanding how Saturn's powerful auroras are generated and sustained. Perhaps the most profound mystery locked in Cassini's final transmission concerns the very heart of the planet. The last gravitational data is allowing scientists to model the structure of Saturn's core with unprecedented detail. The emerging picture is not of a neat, compact ball of rock and ice. Instead, the evidence points toward a fuzzy or diffuse core, a vast region many thousands of miles across where heavier elements are gradually mixing and dissolving into the surrounding envelope of liquid metallic hydrogen. This slow dissolution is more than just a structural curiosity. It is an ongoing process that releases gravitational energy, contributing significantly to the planet's mysterious excess heat. Cassini's death dive is therefore giving us a glimpse into the billion-year process of a gas giant slowly digesting its own core, a fundamental act of planetary evolution we are only now beginning to comprehend. The Cassini mission did not end with a final answer, but with a flood of final questions. Its destruction in Saturn's atmosphere was not an ending, but a transformation. The physical spacecraft is gone, but its legacy lives on in the terabytes of data it faithfully sent home, a dataset so rich that a new generation of scientists will be mining it for discoveries we cannot yet imagine. The final moments of Cassini represent the ultimate paradox of exploration. To truly understand a world, you must sometimes become a part of it. The spacecraft's fiery end was a sacrificial act of inquiry, and the mysteries it revealed in its dying breaths will guide our quest to understand the ringed planet for decades to come. From the incomprehensible geometry of its polar hexagon to the faint, rippling memory of a comet's strike in its D-ring, the world of Saturn is a breathtaking tapestry of interlocking enigmas. We have voyaged together past the churning engine of its internal heat, fueled by a slow drizzle of helium rain deep within its core, and witnessed the fleeting, dazzling spectacle of its rings, actively draining onto the planet in a celestial cascade of ice and complex organics. We have explored moons that are worlds in their own right, from the cryovolcanic jets of Enceladus, venting the secrets of a hidden global ocean, to the methane-soaked landscapes of Titan, where rivers of hydrocarbons carve channels through an icy crust. We have seen the cosmic artistry of gravitational resonances, the shepherding dance of tiny moons that sculpt sharp edges and spiral waves, and the profound mysteries locked within the planet's lopsided gravity and its strangely aligned magnetic field. Each of these 25 puzzles, from the great white storms that erupt with planetary regularity to the alien dual-toned face of Iapetus, is not an isolated phenomenon. They are all threads in a single, complex system, a grand cosmic mechanism where the planet's immense gravity, its internal heat, the physics of its immense magnetic field, and the dynamic interactions with its countless moons all combine to create a reality far stranger and more wonderful than we could have ever imagined from afar. These are not merely curiosities for astronomers, they are the very engines of scientific discovery, the compelling unknowns that push us to build better telescopes, design more daring robotic explorers, and refine our fundamental understanding of physics and chemistry. The lingering question of a habitable ocean within Enceladus directly drives the planning for future missions that will fly through its plumes, searching for the chemical signatures of biology. The mystery of Titan's missing ethane and the source of its methane demands a new generation of landers and orbiters to probe its hidden subsurface aquifers. Every unsolved riddle, from the precise spin of Saturn's deep interior to the ultimate origin of its youthful rings, represents a frontier of human knowledge. Our journey to Saturn has shown us that the more we learn, the more we realize how much we have yet to understand, a humbling and exhilarating realization that fuels our innate desire to explore. Our cosmic neighborhood holds wonders beyond imagination, and the story of Saturn is a powerful reminder that the universe is a place of endless surprise and profound beauty. We've covered 25 of its deepest secrets, but the conversation is far from over. Now we want to hear from you. Which of these mysteries captivates your imagination the most? Is it the potential for life in the dark ocean of Enceladus, or the sheer, unnatural perfection of the North Polar hexagon? Perhaps it's the haunting, ephemeral nature of the rings themselves, a temporary crown we are privileged to witness. Let us know your thoughts in the comments below. If you enjoyed this deep dive into the enigmas of the ringed planet, make sure to subscribe and hit the notification bell. We have many more journeys planned, venturing to the other wonders and unsolved mysteries that await us throughout our incredible solar system.